It's lovely to have you here. Before we begin, I'd love to know, where in the world are you watching from tonight? A quiet bedroom? A sleepy train ride? A cozy couch with a warm cup of tea? Wherever you are, I hope you're comfortable, safe, and ready to gently drift into thought. If you enjoy these relaxing explorations and would like to hear more, a like and subscribe really helps this sleepy little channel float along. And to those of you already subscribed, thank you. Truly. Your support means more than you know. Now, I'll try not to make tonight's topic so interesting that it keeps you wide awake, but if it does, at least you'll have a better understanding of why particles sometimes act like waves and why reality seems to hesitate until someone's watching. A small price to pay for a restless night. So let's begin, shall we? What is quantum physics, and why does it so often sound like the universe is making things up as it goes? The world we know, the one we can see and touch, feels solid, predictable. If you drop a teacup, it falls. If you flip a coin, it lands. If you close your eyes, the moon does not vanish. But in the early 20th century, scientists began to look closer, much closer, and the deeper they peered into the workings of matter, the stranger things became. Light, they discovered, could behave like both a wave and a particle. Particles, it turned out, could exist in many places at once until they were measured. And the act of observing something didn't just reveal what was already there, it seemed to change it. This wasn't a quirk of bad data or fuzzy equipment. It was real, reproducible. And it shattered the tidy laws of classical physics that had held for centuries. Quantum physics wasn't just a new branch of science, it was a new way of seeing reality. A strange and shimmering one, where certainty is replaced by probability, and cause doesn't always precede effect in the way we expect. In this video, we'll drift gently through that world. There's no need to grasp every equation or memorize every name. We'll move slowly, softly, one mystery at a time. From the earliest puzzles that nudge scientists off their classical perch, to the modern questions that still keep physicists up at night. So tuck yourself in, close your eyes if you'd like, and let's begin to explore a world where even emptiness isn't really empty, and where everything you thought you knew about reality is only probably true. At the turn of the 20th century, physics felt almost complete. The laws of motion were understood, thermodynamics was tidy, and light was nicely tucked into the framework of electromagnetic theory. It was a golden age of certainty. Some scientists even believed that all the big questions had already been answered. Only a few odd bits remained to be cleaned up, like dust in the corners of a well-swept room. One of those dusty corners involved a very simple idea. What happens when you heat up an object? When you warm a piece of metal or a lump of coal, it glows, first red, then orange, then white, depending on the temperature. This glow, called black body radiation, comes from how objects emit electromagnetic radiation when heated. It was easy to observe, and it seemed like it should be easy to explain. And yet, the math refused to cooperate. Classical physics, using the well-known equations of the time, predicted something bizarre. According to the formulas, as the temperature of a black body increased, it should emit more and more energy at shorter and shorter wavelengths, particularly in the ultraviolet range. The problem: this prediction led to infinite energy at high frequencies, a scenario so impossible and ridiculous it was nicknamed the ultraviolet catastrophe. No amount of tweaking classical equations could stop the math from spiraling into nonsense. Reality simply didn't match the predictions. Something was missing. Enter Max Planck. In 1899, Planck was a German theoretical physicist with a reputation for careful thinking. He wasn't particularly radical or rebellious. In fact, he firmly believed in the classical worldview, but he was also pragmatic, and when faced with the blackbody radiation problem, he did something quietly revolutionary. To fix the math, Planck introduced a small, strange idea. What if energy couldn't be emitted in just any amount? What if, instead, it came in tiny, indivisible packets? Like coins you can't split in half, these packets would represent the smallest possible units of energy. He called these packets quanta. This was a dramatic shift from the continuous view of energy held by classical physics. Instead of a smooth flow, energy would arrive in steps, tiny jumps that depended on the frequency of the radiation. Planck even introduced a constant, now known as Planck's constant, to describe the size of these energy packets. It was unimaginably small, but mathematically elegant. When he plugged this idea into his equations, something amazing happened. The infinite energy problem vanished. The equations worked. They matched the real world. Planck had solved the ultraviolet catastrophe. And yet he didn't quite believe it. In fact, Planck himself described his solution as a mathematical trick, a clever way to make the numbers behave, but not a description of how the universe actually worked. He assumed that future physicists would find a better explanation that wouldn't require such odd assumptions. Quantization, to him, was a temporary patch, not a fundamental truth. What he couldn't have known at the time was that his trick would become the cornerstone of an entirely new way of thinking. His idea that energy comes in discrete packets laid the groundwork for quantum theory, a theory that would soon unravel much of what classical physics had taken for granted. It's easy to look back and see this as the moment everything changed, but at the time it felt more like a strange side note than a revolution. Planck hadn't set out to challenge the foundations of physics, he just wanted the math to work, and yet, by introducing quantization, he had lit the first match in what would become a slow-burning fire, one that would eventually reshape our understanding of light, matter, and the nature of reality itself. This humble beginning, tucked into a quiet paper published in 1900, didn't shout its importance. There were no dramatic declarations, no sweeping pronouncements, just a small constant, a new way of thinking about energy, and a curious little fix for a problem that refused to go away. From that point on, physics would never quite feel finished again. By the early 1900s, light was thought to be pretty well understood. Thanks to James Clerk Maxwell's equations, scientists had shown that light behaved like a wave, an elegant ripple in the electromagnetic field. It bent, bounced, diffracted, and interfered just like any proper wave should. And after Max Planck's quiet introduction of energy quanta, most physicists assumed things would settle down into a new, slightly adjusted normal. But then came a riddle involving metal, light, and a surprising refusal to cooperate. It was called the photoelectric effect, and it worked like this. If you shine light on a metal surface, electrons can be ejected from the metal. The idea made sense. Light delivers energy. Energy kicks out electrons. No big deal. According to wave theory, increasing the brightness of the light should increase the energy transferred to the electrons. A brighter wave should shake electrons loose more effectively. That was the expectation. But that's not what happened. In experiments, scientists found something strange. Shining brighter light didn't necessarily eject electrons with more energy. What mattered most was the frequency of the light. If the light was below a certain frequency, even a very bright light, it did nothing at all. No electrons were ejected, but above that frequency, even a dim beam could knock electrons free with ease. The threshold was sharp and it made no sense under classical wave theory. This little inconsistency became a full-blown mystery. Enter Albert Einstein. In 1905, a year often called his miracle year, Einstein published a paper that changed everything. To explain the photoelectric effect, he proposed something bold. What if light wasn't just a wave? What if, under certain circumstances, it behaved like a particle, a tiny bundle of energy travelling in a straight line? Einstein suggested that light was made of individual packets of energy, which he called quanta of light, later known as photons. Each photon carried a specific amount of energy, determined by its frequency. If a photon had enough energy, it could knock an electron loose from a metal surface. If it didn't, no amount of photons, no matter how many or how bright, could do the job. It was like trying to open a locked door with a handful of keys, none of which fit. no matter how many you had, you weren't getting in. Einstein's idea built directly on Planck's earlier work, but went further. He wasn't just using energy packets as a mathematical trick. He was suggesting that light itself was made of these packets, not as a convenient fiction, but as a literal description of how light behaves. It was a revolutionary claim, and not everyone liked it. Many physicists clung tightly to the wave model of light. After all, light clearly did exhibit wave-like behavior. It diffracted around corners. It created interference patterns. If light was really made of particles, how could it also behave like a wave? Einstein didn't deny the wave nature of light. Instead, he proposed something stranger. Light, he said, was both a wave and a particle. It could act like one or the other, depending on how you observed it. This duality wasn't just a weird trick of perception, it was fundamental to the nature of light itself. Imagine a beam of sunlight filtering through a window. It spreads and ripples like a wave bouncing off dust and glass. But zoom in, way in, and you'd find tiny quanta of energy, each with its own frequency, knocking into atoms, changing the world one collision at a time. This idea of wave-particle duality is one of the strangest in all of physics, not because it's complicated, but because it challenges the very categories we use to describe reality. In the classical world, things were either particles or waves, not both, not neither, and certainly not whatever they feel like being depending on the situation. But the quantum world doesn't ask permission to make sense. Einstein's photon explanation of the photoelectric effect not only matched the experimental results, it did so beautifully. The energy of each photon depended on its frequency, exactly as Planck had suggested, and it neatly explained why low-frequency light, no matter how intense, couldn't eject electrons. The individual photons simply didn't carry enough punch. The impact of this idea was massive. In 1921, Einstein received the Nobel Prize in Physics, not for relativity as many assume, but for his explanation of the photoelectric effect. That's how significant this discovery was. Still, even Einstein found the quantum world uncomfortable. He famously resisted the more probabilistic interpretations that would follow in later years. God does not play dice with the universe, he once declared. But dice or not, the rules were changing, and at the heart of those changes was a strange truth. Light, the thing that illuminates our world, refused to fit into any tidy box. It came in quanta. It danced as a wave. It collided like a particle. It shimmered between states, revealing just enough to keep us wondering and just enough to keep us unsure. What began as a simple experiment with light and metal ended up shaking the foundations of physics. Because if light could behave this way, both continuous and discrete, both spread out and point-like, what else might be lurking in the quiet corners of the universe waiting to break the rules? Imagine this. You set up a table, place a flashlight at one end, and cut two tiny slits in a piece of cardboard. You shine the light through the slits, and look at the pattern it makes on a screen behind them. Not exactly thrilling, right? And yet in this humble arrangement, 2 holes and a bit of light, we find one of the most mind-bending experiments in all of science. The double-slit experiment has become something of a legend in physics, and not because it's complicated. In fact, it's almost embarrassingly simple. But what it reveals is anything but. Some physicists have even joked that this is the most dramatic science experiment of all time, starring a flashlight and 2 holes in cardboard. Let's start with what we'd expect. In the world of classical physics, waves and particles behave very differently. A wave, like water or sound, spreads out. It interferes with itself. Imagine ocean waves passing through 2 openings in a barrier. The waves emerge on the other side and overlap, creating a pattern of peaks and troughs that can reinforce or cancel each other out. That's interference. It's well understood and predictable. Now imagine particles, like tiny rubber balls, fired at a wall with 2 openings. Some go through the left slit, some go through the right. They don't overlap or interfere. On the screen behind the slits, you'd expect to see 2 clusters of impact points, right where the slits are. That's the particle behavior. Straightforward, no surprises. So what happens when you do this with light? When scientists first shined light through the two slits, they expected it to behave like a wave, and it did. The light spread out and formed an interference pattern, a series of bright and dark bands on the screen caused by the wave peaks overlapping and cancelling each other in specific places. So far, so good. Light, as Maxwell had predicted, was behaving like a wave. But then things got weird. Using very sensitive equipment, researchers turned down the intensity of the light source until it was firing just one photon at a time. Instead of a constant stream, there were individual particles of light making their way toward the slits, one by one. Now you'd expect these lone photons to act like particles, each going through one slit or the other, and if you wait long enough and collect enough hits on the screen, you should see two bright spots where the particles landed just like those rubber balls. But that's not what happened. Even when sent through one at a time, the photons gradually built up the same interference pattern as before, a pattern that required waves interfering with themselves. But how could a single photon interfere with itself? Did it go through both slits at once? Was it somehow a wave and a particle at the same time? This was no illusion. The interference pattern persisted, suggesting that each photon had travelled through both slits simultaneously, like a ghost of itself, exploring every possible path, until it landed. If that wasn't enough to raise some eyebrows, things got even stranger. Physicists decided to peek behind the curtain. They placed detectors at the slits to observe which path the photon actually took. Surely, they thought, we can just watch and settle this once and for all. Did the photon go through the left slit, the right slit, or somehow both? But when they looked, the interference pattern vanished. As soon as the detectors were turned on and the photons were observed, the photons stopped behaving like waves. They acted like ordinary particles again, landing behind just one slit or the other. No more interference, no more ghostly wave behaviour. It was as if the very act of observing forced the photon to make a decision. Go left or go right. No superpositions, no fuzzy in-betweens. Reality had been caught in the act, and it immediately straightened up and acted normal. Turn off the detectors, and the interference returned. Turn them back on, and it vanished again. The implications were staggering. It wasn't that our measuring devices disturbed the photons. These were passive, non-intrusive setups. The issue wasn't how we observed, but that we observed at all. It seemed that the mere knowledge of the photon's path, the potential to know, was enough to collapse its wave-like behaviour into a particle state. Reality, in a sense, cared whether it was being watched. This wasn't just a fluke or experimental error. The double-slit experiment has been repeated countless times, with photons, electrons, even molecules made of hundreds of atoms. Always, the result is the same. Left unobserved, these particles act like waves and interfere with themselves. Observed, they behave like classical particles and fall neatly into line. And if that sounds unsettling, well, you're not alone. This experiment sits at the very heart of quantum physics, and it resists every effort to explain it in familiar terms. It suggests that at the smaller scales, particles don't follow strict paths. Instead, they exist as a spread of possibilities, a shimmering cloud of potential outcomes. Only when a measurement is made does that cloud collapse into something definite. Some have tried to picture the photon as a wave that splits and reunites. Others prefer the language of probability, describing the wave function as a tool for predicting outcomes. And still others, in the many worlds camp, imagine each possibility branching into its own separate universe. But whatever the interpretation, the facts remain the same. Until we observe it, the particle doesn't seem to commit to any one state. What began as a simple test of light has turned into a profound mystery about the nature of reality itself. Is observation an active part of shaping the universe? Does information have power over existence? Is reality fundamentally uncertain until we ask it to reveal itself? These aren't just philosophical questions, they're scientific ones, rooted in experiment, measured and confirmed. The double-slit experiment doesn't give us clear answers, but it does give us one powerful insight. The universe, at its core, is not a clockwork machine. It's a strange and shimmering tapestry, woven from possibilities, and it responds in curious ways to our gaze. With two slits, a light source, and a screen, we've discovered that the universe winks at us when we're not looking, and stands still when we are. In the world of quantum physics, if there's one piece of math that's whispered through the entire theory like a secret spell, it's Schrödinger's equation. Now, don't worry, this isn't going to be a math lecture. No one's getting out of bed to dream about partial differential equations. But this particular equation is different. It's not just a string of symbols scribbled on a chalkboard, it's the quiet heartbeat of the quantum world. Back in the 1920s, physicists were wrestling with how to describe particles that didn't seem to behave like particles at all. Electrons were showing wave-like patterns, photons were acting like probabilistic ghosts, and the old laws of motion, the ones Newton gave us, just weren't cutting it anymore. The universe needed a new kind of language. Enter Erwin Schrödinger. In 1926, he proposed an equation that described not just how particles moved, but how their wave functions evolved over time. It was elegant, compact, and shockingly effective. And even though it might look like a tangle of Greek letters and operators, at its core it tells a simple story. It describes how a quantum system changes. But let's step away from the symbols and get to what really matters. The key concept here is the wave function, often denoted by the Greek letter psi. If that sounds abstract, think of it like this. The wave function is a sort of mathematical whisper that tells us everything we can know about a quantum system, where a particle might be, how likely it is to be there, how it's moving or might be moving. The wave function doesn't give us hard answers, it gives us probabilities. If you picture a particle as a little dot moving through space, classical physics will draw a neat arrow showing its exact position and velocity. Schrödinger's world doesn't do that. Instead, it gives us a hazy, rippling cloud, a wave, that says, the particle is likely to be over here, but it could also be over there, and maybe just a little bit up there too. This is where the magic happens. Schrödinger's equation lets us evolve this cloud over time. It shows how the wave function changes as the particle moves, though it's really more like how the possibilities of its position shift and flow. And when we measure the particle, when we ask, "Where are you?" that wave function collapses. Suddenly the cloud disappears and we get a single definite answer. Here it is, right there, but only after we've looked. This wave-based view of reality is profoundly different from the mechanical picture of the universe that came before. Instead of particles tracing predictable paths like planets around the sun, we now see swirling fields of probability full of uncertainty and ambiguity until observation pins them down. But let's pull it down to something more visual. Imagine you're blindfolded and standing in a room. Somewhere in that room there's a quiet cat. You can't hear it, can't see it, but you can toss little balls and listen for the sound they make when they land. Over time, you start to build a picture of where the cat might be. Areas with a higher chance, others with less. That mental map you're building, that's like the wave function. It's not a picture of reality as it is, but as it might be. Now imagine you could write an equation that tells you how your map changes over time. Maybe the cat likes to move toward corners or sit near warm objects. That equation would be your guide to where the cat is likely to be next. That's what Schrödinger did, except instead of cats, he was thinking about electrons. The actual equation is continuous and smooth. It allows these waves of probability to ripple and shift just like water in a pond. It respects the underlying symmetries of nature, like energy conservation and time evolution, but it doesn't care much for certainty. It tells us what could happen, not what will happen. And what's fascinating is how beautifully it works. Physicists have used Schrödinger's equation to describe everything from the structure of atoms to the way molecules bond, from semiconductor behavior to superconductors. It even predicts exotic phenomena like quantum tunneling, where particles slip through barriers they shouldn't be able to cross. The equation itself is timeless. gently ticking forward with every moment, offering a map of the unknowable. One of its most famous successes was in explaining the hydrogen atom, the simplest atom in the universe. Before quantum mechanics, no one could fully explain why electrons around a nucleus seem to settle into specific orbits, rather than spiraling inward or wandering off. Schrödinger's equation revealed that electrons aren't whizzing around like miniature planets. Instead, they form standing waves, stable patterns of probability, around the nucleus. These are the orbitals you may have seen drawn as soft clouds or shapes in textbooks. And these clouds are not just visual metaphors, they represent the real measurable likelihood of where an electron might be found if you decided to look. These aren't orbits, they're presence zones, and they exist only because the electron isn't a simple particle. It's a ripple in a sea of probabilities. It's strange, certainly, but it's also beautifully consistent. Unlike some theories that need patches or caveats, Schrödinger's equation has aged like fine wine. It works. It has predicted time and again the behaviour of the very small with astonishing accuracy. And yet it remains hauntingly abstract. You can't hold a wave function. You can't see it. But it's there, describing the ghostly potential of everything from an atom in your tea to the electronics in your phone. And then there's the philosophical side. What is a wave function, really? Is it a description of our knowledge? Or is it an actual part of reality? Something that truly exists until it collapses into one outcome? Different interpretations of quantum mechanics argue fiercely about this. But the equation itself doesn't take sides. It simply does what it does, quietly, reliably, and strangely. Even Schrödinger himself had mixed feelings. While he was proud of the equation, he disliked the idea that particles didn't have definite properties until they were observed. His famous thought experiment involving a cat, alive and dead at the same time, was meant as a critique of the very uncertainty his work had unleashed. He gave us the mathematics of quantum waves, then questioned what those waves really meant. Still, it's hard not to admire what he built. In a world that often demands yes or no here or there, Schrödinger offered something gentler, a shimmer of maybe, a softly pulsing guide to what could be. His equation doesn't shout or command, it suggests, it flows. And in doing so, it reveals a version of the universe that's quieter, subtler, and far more mysterious than we ever imagined. At the tiniest scales, motion isn't always motion, position isn't always position, and certainty is more of a luxury than a rule. But thanks to one elegant equation, we can still find our way, gently, mathematically, through the haze. In the classical world, the world of apples, bicycles, and bowling balls, you can know where something is and how fast it's going at the same time. It's not even a question. A radar gun clocks the speed of a car while GPS tells you exactly where it is. No mystery, no contradiction. But the quantum world doesn't play by those rules. In the 1920s, Werner Heisenberg introduced a principle so strange and so central to quantum mechanics that it still gives students and scientists alike a moment of pause. It's called the uncertainty principle, and it tells us that at the most fundamental level of reality, there are limits to what we can know. Specifically, it says this: the more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. Now, momentum is just mass times velocity. It's a measure of how much motion something has, and if you think about it in everyday terms, this principle sounds almost silly. How could knowing where something is make you unsure about how fast it's going? If you see a train pulling into the station, you know both its position and its speed. Easy. But at the quantum scale, reality doesn't allow that kind of clarity. This isn't about our measuring tools being clumsy or crude. It's not a matter of needing better technology. The uncertainty isn't in our instruments. It's woven into the fabric of the universe itself. Let's say you're trying to observe an electron. You want to know where it is and how fast it's moving. To do that, you might shine some light on it. But light is made of photons, and photons carry energy. When one of those photons hits the electron, it changes the electron's motion. It's a bit like trying to find a soap bubble in the dark by throwing tennis balls at it. You'll definitely find it, but you'll also destroy it in the process. Still, Heisenberg's point wasn't just about disturbing particles. His principle is built into the mathematics of quantum mechanics. Even if you could observe without interfering, watching through some ghostly, non-intrusive means, the uncertainty would still be there. It's not a bug, it's a feature. At the heart of the uncertainty principle is the wave nature of particles. Imagine trying to locate a wave in the ocean. You can say where the crest is, but the wave stretches out in space. Similarly, a particle like an electron is described by a wave function, a spread-out cloud of possibilities. If the wave is wide and smooth, you can't tell where the particle is exactly, but you can estimate its momentum fairly well. If you narrow the wave to pinpoint the particle's position, the momentum becomes more uncertain. The wave gets choppy. It's a cosmic trade-off, and there's no way around it. The product of the uncertainty in position and the uncertainty in momentum is always greater than or equal to a tiny number. Planck's constant, divided by 4 pi. That number is very small, so in our everyday world the effect is negligible. You can measure the position and speed of a baseball to incredible precision without ever bumping into quantum limits. But at the scale of electrons, atoms and subatomic particles, the uncertainty becomes impossible to ignore. It shapes the very behavior of the world beneath our senses. If you try to trap a particle in a very small space, to nail down its position, it starts to behave wildly. Its momentum becomes highly uncertain, and it can begin zipping around unpredictably. Try to pin it down further, and it resists even more. It's as though nature doesn't like being told exactly where things are. This is not an error in the machinery, it's a blur that can't be wiped away. One way to think about it is like trying to hold mist in your hands. The tighter you squeeze, the less you have. Open your hands a little, and more of it lingers. That's the delicate balance between knowing too much and being forced to let go of something else. In many ways, the uncertainty principle is a philosophical warning label on the quantum world. It tells us that knowledge has boundaries, not because of human limitations, but because of how reality itself is built. We're not dealing with tiny billiard balls rolling through space. We're dealing with possibilities, probabilities, and waves that refuse to be nailed down too tightly. This principle also explains why atoms don't collapse. You might wonder why electrons don't simply fall into the nucleus of an atom, since opposite charges attract. But thanks to the uncertainty principle, electrons can't sit still. If an electron were to fall into the nucleus and stay there, its position would be perfectly known, which means its momentum would become infinitely uncertain. That would require infinite energy. Nature says no. So electrons hover, not because they want to, but because quantum rules won't allow anything else. The uncertainty principle creates a kind of built-in resistance, a gentle pushback against absolute confinement. This strange limit also has consequences for measurements of energy and time, or angular momentum and orientation. In each pair, increasing precision in one means surrendering certainty in the other. It's a universal truth at the quantum level, and yet there's something comforting about it too. Uncertainty in this sense is not chaos. It's not randomness run wild. It's a structured ambiguity, a kind of graceful fuzziness. It gives the universe its texture. It allows particles to tunnel through barriers, atoms to be stable, and chemistry to happen. Without it, reality might be too rigid to support life at all. So much of science has been about finding certainty, predicting, measuring, knowing. Heisenberg's insight flipped that desire on its head. He showed that some aspects of nature will always remain just out of reach, and that's not a failure, it's just how things are. In a strange way, the uncertainty principle invites us to make peace with not knowing, to sit quietly with the blur and appreciate the softness of what lies beneath the surface. It's a reminder that the deepest truths are not always sharp-edged but cloudy, rippling and unresolved. And perhaps that's exactly why they're so beautiful. In our everyday experience, things tend to be in one state or another. A coin lands heads or tails, a light switch is on or off. Your tea is hot or cold, though sometimes questionably lukewarm. But in the quantum world, this tidy division of states breaks down completely. Objects at the smallest scales don't always pick a side. They can hover in a strange in-between, a blend of all possible outcomes. This is the realm of quantum superposition. To picture this, imagine flipping a coin. In the classical world, once the coin leaves your hand, it travels through the air with a clear trajectory. You may not know whether it's heads or tails until it lands, but it is one or the other the whole time. It's just hidden from you. Quantum systems don't work that way. In the quantum world, if you flip a quantum coin, it doesn't secretly land on one side while you're not looking. Instead, it enters a state of superposition, a weighted combination of both heads and tails at once. It isn't undecided, it isn't switching quickly between the two. It is genuinely, physically in a state that is both, until you observe it. And when you do, when you check to see what state the system is in, the superposition collapses. The quantum coin chooses a face, and your measurement becomes real. But before you looked, it wasn't just unknown. It was both. That's a hard pill to swallow, and it's not just counterintuitive, it's deeply weird. Superposition was first introduced as a way to describe the behavior of quantum particles like electrons and photons. These particles, rather than following predictable paths, exist as wave functions, mathematical expressions that describe probabilities. Each possible state, a spin pointing up or down, a photon going left or right, is part of the equation, and all those possibilities coexist until a measurement selects one. You might picture it like a foggy landscape of outcomes. The particle isn't walking a path, it's more like it's spread out, smearing itself across every possible route it could take. When you interact with it, that fog suddenly snaps into a single location, a specific outcome, like lightning illuminating one hilltop in the mist. This concept led to one of the most famous thought experiments in all of physics, Schrödinger's cat. Suppose you place a cat in a sealed box with a radioactive atom, a detector, and a vial of poison. If the atom decays, the detector breaks the vial and the cat dies. If it doesn't, the cat lives. Quantum mechanics tells us that until the atom is observed, it exists in a superposition of decayed and not decayed states. And so, by extension, the cat is both alive and dead until someone opens the box. This wasn't meant to be taken literally. Erwin Schrödinger was highlighting the absurdity of applying quantum rules to large objects. But the idea struck a chord. It painted superposition not just as an abstract idea, but as something with deeply strange implications for what reality is. And yet, despite all the weirdness, superposition is not a flaw in the theory. It's not some bizarre loophole that physicists tolerate. It's one of the most powerful features of quantum mechanics. In fact, much of modern quantum technology depends on it. Take quantum computing, for example. In a classical computer, the smallest unit of information is the bit, which can be either 0 or 1. Everything your phone or laptop does, every photo, every song, every message, is encoded using combinations of these two states. Quantum computers use qubits instead, and a qubit, unlike a regular bit, can exist in a superposition of both 0 and 1 at the same time. It's not switching between them, it's genuinely in a mixture of both. This means that a single qubit holds more information than a classical bit, and when multiple qubits are entangled, they can represent a vast number of states simultaneously. This allows quantum computers to perform certain calculations far more efficiently than classical ones. It's not magic, it's just math that plays by quantum rules. Problems involving complex systems like simulating molecules or optimizing large networks suddenly become tractable, and it all hinges on the ability of qubits to be in superposition. Superposition also appears in quantum cryptography, where it helps ensure that information can't be intercepted without being noticed. In quantum sensing, it allows scientists to detect extremely small changes in magnetic or gravitational fields. These aren't sci-fi dreams, they're real technologies being developed right now. But there's a twist. Superposition is delicate. Quantum systems are easily disturbed. The slightest interaction with the environment, stray photons, vibrations, even air molecules, can collapse the wave function. This process, known as decoherence, is one of the biggest challenges in building stable quantum systems. It's like trying to balance a feather on the tip of a pencil while someone's sneezing in the next room. The superposition vanishes the moment the system interacts with the outside world. That fragility is part of what makes quantum systems so fascinating. They offer power, but only under very precise and isolated conditions. They give us access to probabilities, not certainties, and ask us to rethink what it means to say that something is. It also leads to a deeper philosophical question. If particles can exist in multiple states, is that reality, or just a reflection of what we know? Some interpretations suggest that the wave function represents knowledge, our best guess about a system until we measure it. Others say the wave function is physically real, and the particle truly is in multiple states until it's forced to choose. Either way, quantum superposition invites us to loosen our grip on classical logic. It tells us that opposites can coexist, that a system can be this and that, here and there, yes and no, all at once. That reality, at its core, is not a single thread, but a tapestry of possibilities, overlapping and unresolved until observation pulls one strand loose. It's strange, it's uncomfortable, but it's also beautiful. Because in this strange rule of superposition, we find a universe that isn't rigid, but flexible. Not mechanical, but poetic. It's a world that allows for contradiction and uncertainty, not as flaws, but as features. And in doing so, it opens up new ways to compute, to communicate, to explore, and to imagine what's possible when reality refuses to make up its mind. Imagine you have two gloves, one left-handed and one right-handed. You put each glove into a separate box and send one to the other side of the world. You don't know which box contains which glove, but the moment you open one and see a left-handed glove, you instantly know the other must be right-handed. It's not mysterious, it's just logic. The gloves were always one left, one right. No drama there. But quantum entanglement isn't like that. Entangled particles aren't like pre-packed gloves. They're more like a pair of gloves that don't decide which hand they are until after you open one of the boxes, and whichever one you open first somehow tells the other how to behave instantly, no matter how far apart they are. It's not just that the outcome is correlated, it's that the properties don't seem to exist until the moment you measure one of them, and the act of measuring one instantly affects the other. This is the phenomenon of quantum entanglement, and it is one of the strangest, most baffling features of the quantum world. Here's how it works. When two particles interact in a certain way, by being created together, colliding, or otherwise becoming connected, they can become entangled. That means their quantum states become linked. Whatever happens to one, in a very real sense, affects the other, even when they are separated by great distances. Imagine creating two entangled photons whose polarizations are uncertain until measured. One might end up polarized vertically, the other horizontally. But they don't decide ahead of time who gets which. They stay in a shared quantum state, a superposition of all possibilities. Only when you measure one does the outcome become definite, and at that moment, the other state becomes definite too. Instantly, no signal, no delay, no chance to communicate. If you measure one photon in Paris, the other, let's say it's in Tokyo, responds at that very moment, as though the universe just updated both of them simultaneously. This is what Einstein famously called spooky action at a distance. Einstein wasn't fond of spooky things. He believed firmly in locality, the idea that physical processes at one location can't instantly affect things far away. It's a cornerstone of relativity. Nothing, not even information, travels faster than light. The idea that two particles could coordinate outcomes instantaneously, without exchanging a signal, made him deeply uncomfortable. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper challenging the completeness of quantum mechanics. They argued that if quantum mechanics allows for such instantaneous connections, it must be missing something, some hidden variables tucked behind the scenes, determining the outcomes all along. To Einstein, the universe should be predictable, orderly, and perhaps most importantly, local. But decades later, experiments began to confirm what quantum theory had predicted all along. Entanglement is real, and those hidden variables, they never showed up. In the 1960s, physicist John Bell devised a testable mathematical inequality, now known as Bell's theorem, that could distinguish between quantum predictions and hidden variable theories. And when physicists performed these experiments again and again, quantum mechanics won. Entangled particles do behave in ways that can't be explained by local hidden variables. The results are random, yet perfectly correlated. It's as if the particles share a private script, one that remains unwritten until the curtain rises, and they improvise together with eerie perfect timing. Still, this doesn't mean you can use entanglement to send messages faster than light. That would break causality, and thankfully, nature prevents it. While entangled particles react instantly to each other's measurements, the outcomes are fundamentally random. You can't control what result you get when you measure your particle, which means you can't encode information in it. The instant connection is real, but it can't be used for communication. It's like two people flipping coins on opposite sides of the galaxy. Each result is random, but somehow, when one person flips heads, the other always flips tails, and neither of them knows which it will be until they flip. They aren't sending messages, they're just in sync in a way that defies space. What's truly strange is that this connection doesn't weaken with distance. You could separate two entangled particles by the width of a room, a continent or a light year, and the entanglement would remain. There's no known limit. In fact, physicists have entangled particles over distances of hundreds of kilometers using satellites, and the results continue to uphold quantum theory. But what exactly is entanglement? Is it a kind of invisible tether? A shared identity across space? A subtle form of information smeared between particles? The truth is, no one's completely sure. Different interpretations of quantum mechanics offer different perspectives. Some see entanglement as a reflection of information, what we know about the system, not the system itself. Others see it as evidence of a deep, non-local fabric to reality. There's even a school of thought that entanglement isn't just a quirky quantum trick, but a fundamental feature of space and time themselves. Some researchers have proposed that space-time, the very geometry of the universe, might emerge from networks of entanglement between tiny quantum bits. If that's true, entanglement isn't something that happens in space. It's what holds space together. That's a bold idea, and one still under investigation. But it hints at just how central entanglement may be, not just to particles, but to the nature of reality. And like many quantum ideas, it's not just theoretical. Entanglement has practical applications. It's the foundation for quantum teleportation, not the Star Trek kind, but the real-world transfer of quantum states from one place to another. It also underlies quantum key distribution, a method of secure communication that guarantees privacy. If an eavesdropper tries to intercept the key, the entanglement is disturbed and the interference is immediately detectable. In quantum computing, entanglement allows for complex operations involving many qubits that can't be reduced to simple individual actions. It's part of what gives quantum computers their power, not just more speed, but more interconnection, a kind of parallelism that ordinary computers can't match. So this spooky action, once a source of deep unease, is now a cornerstone of cutting-edge technology. Einstein may have disliked it, but even he couldn't deny its mathematical consistency. And while relativity and quantum mechanics still haven't been fully unified, both remain astonishingly successful in their respective realms. Entanglement reminds us that the universe is not simply a collection of independent objects bouncing around. It is a deeply interconnected web where even distant elements can be parts of a shared whole, where separateness is, at times, an illusion. It's not something we see in daily life. You don't wake up entangled with your neighbour or find your coffee reflecting the state of someone else's spoon. But at the tiniest levels, this silent partnership between particles is quietly humming away, everywhere, all the time. And maybe that's the strangest part of all, that even in a universe of stars and silence, of vast distance and emptiness, there are still echoes of togetherness, instant, invisible, and unshakably real. There are few animals in science more famous than Schrödinger's cat. This curious feline has become the unofficial mascot of quantum physics, a creature trapped in a thought experiment so peculiar that it's often mistaken for satire. And in a way it is. It was never meant to be taken literally, but like all good metaphors it touches on something deeper, a quiet discomfort at the heart of quantum mechanics. The story begins in the 1930s when physicists were grappling with what quantum theory actually meant. The math worked, the predictions were accurate, but what was it saying about the world? Was the wave function a real thing? Did particles really exist in multiple states until they were measured? Or was this just a tool for calculating outcomes? Erwin Schrödinger, already famous for his elegant quantum equation, was deeply skeptical of how far some physicists were willing to push the idea of superposition, especially when it came to measurement. In his view, there was something fishy about applying the same rules that governed electrons to everyday objects, like, say, a cat. So he posed a question, a dark, playful question. What happens if you take the weirdness of quantum mechanics and scale it up to something you can hold in your arms? Imagine a sealed box. Inside the box is a cat. Alongside the cat is a tiny radioactive atom, a Geiger counter, a vial of poison, and a trigger mechanism. If the atom decays, something quantum mechanics tells us happens at random, the Geiger counter detects it. The trigger breaks the vial and the poison is released. The cat tragically dies. But here's the twist. Quantum theory tells us that until we observe the atom, it exists in a superposition of both decayed and not decayed states, which means the entire system, the detector, the poison, and yes, the cat, should also be in a superposition. The cat is both alive and dead. Not metaphorically, literally, at least according to some interpretations. Of course, no one has actually put a cat in a quantum box. Schrödinger wasn't proposing an experiment. He was making a point. He found it absurd to think that a cat, an animal with whiskers, warmth, and a clear preference for naps, could exist in such a blurry, undefined state. It wasn't just strange, it was nonsense. And yet the idea stuck, partly because it captured the essence of quantum indeterminacy in a single, unforgettable image. A cat that is both dead and alive until the box is opened. That's a powerful way to express what it means for a system to remain unmeasured. It's not about indecision, it's about possibility. Until observation collapses the wave function, the system contains every outcome, all futures, all states, simultaneously. Schrödinger's cat isn't really about cats, it's about what we're allowed to say about the world before we've looked. In quantum mechanics, observation plays a central role. Before you measure a system, it exists in a cloud of probabilities, each possible state encoded in the wave function. But the moment you interact with it in a way that extracts information, that cloud collapses, the system picks a state. One possibility becomes real, all others vanish. But here's the tricky part. What exactly counts as a measurement? Is it the presence of a conscious observer, a mechanical detector, an interaction with the environment? Different interpretations give different answers, and that ambiguity is part of why the cat still gets so much attention. It forces us to confront the fact that quantum theory, while breathtakingly successful in predicting outcomes, is oddly silent about what's really happening in between. Some physicists lean on the Copenhagen interpretation, which essentially says don't worry about it. The wave function tells us everything we can know, and measurement simply reveals what's already latent in the system. Others prefer the many worlds view, where the cat is both alive and dead in separate branching universes, and opening the box doesn't collapse the wave function, it merely selects your path through the multiverse. There's also the decoherence approach, which argues that interaction with the environment naturally filters out superpositions, leaving systems that appear classical. In this view, the cat is never truly in a limbo state, just entangled with so many environmental variables that we can't track them all. The superposition becomes inaccessible, not non-existent. Each perspective carries its own philosophical baggage, but all agree on this. Quantum systems do not behave like miniature classical objects. They don't sit still and wait to be discovered. They evolve, probabilistically in complex and often non-intuitive ways. So what does this mean for the cat? It means the box isn't just a container, it's a boundary between the quantum and classical worlds, a stage on which the rules of physics twist into something weirder, where questions like, is the cat alive, don't have simple answers. Instead, we have to say the cat is in a superposition of states, alive and dead, until we open the box and collapse that ambiguity into something definite. And that's what makes the cat a perfect metaphor for unmeasured systems. In the quantum world, systems evolve according to the Schrödinger equation. But that evolution doesn't pick a path. It explores all possible paths at once. An electron doesn't travel from point A to point B, it spreads through every route, every detour, until we observe it and reduce that blur to a single outcome. The cat in the box is just a macroscopic way of expressing that. The difference is scale, not principle, and that's what troubled Schrödinger. If the theory truly applies to everything, then at some level, everything, including us, is part of a superposition. Which leads to one final, somewhat unsettling question. What if the observer is part of the system? If opening the box collapses the cat's wave function, what collapses ours? Where does the observer line stop? Are we just another link in a long quantum chain, collapsing probabilities as we go? Or are we simply riding the wave, surfing on probabilities, never quite sure where the next collapse will take us? In the end, Schrödinger's cat isn't just about life and death. It's about knowledge and the strange dance between reality and observation. It's about what it means to say something is, when the very act of saying so might change the outcome. It's a reminder that in the quantum world, certainty is rare, clarity is conditional, and sometimes the universe waits for us to peek inside the box. In the everyday world, walls are pretty straightforward. If you throw a tennis ball at a wall and it doesn't have enough energy to get through, it bounces off. Simple, predictable. The universe says, "Nice try," and your ball obeys the rules of classical physics like a well-behaved object. But in the quantum world, predictability takes a holiday. In this strange realm, a particle can hit a wall, not have enough energy to pass through, and yet still show up on the other side. No smashing, no breaking, no squeezing through cracks. It simply appears as if it decided the obstacle wasn't quite as solid as it looked. This phenomenon is called quantum tunneling, and it's one of those effects that makes you blink, rub your eyes, and wonder if the laws of physics are having a laugh. But tunneling is very real, it's measurable, predictable, and fundamental to how the universe works, and surprisingly, it all comes down to probability. To understand tunneling, we need to revisit the concept of wave functions. In quantum mechanics, particles like electrons aren't just little dots zooming around, they're described by wave functions that represent a spread of possible positions. These waves can extend across space, fading gradually instead of stopping abruptly. This means that even if there's a region the particle technically shouldn't be able to reach, the wave function might still stretch into that forbidden zone, albeit faintly. Now, imagine a particle approaching a barrier, a region with more energy than the particle itself has. In classical physics, this would be a hard stop, game over. But the quantum wave function doesn't vanish at the barrier. It tapers off like a whisper fading through a wall. and if the wall isn't too wide or too tall, that whisper can make it to the other side. The particle might not have enough energy to climb over the barrier, but its wave function can tunnel through, and if part of the wave function makes it to the other side, there's a small but non-zero probability that the particle itself will show up there too. But it's not magic, it's math. This idea sounds abstract, but it has very concrete consequences, especially when you shrink your thinking down to the atomic scale. Take radioactive decay, for example. Some atomic nuclei are unstable, and one of the ways they become stable is by ejecting particles, like alpha particles made of 2 protons and 2 neutrons. These particles are trapped inside the nucleus by a powerful nuclear barrier. According to classical physics, they don't have enough energy to escape, but they do escape, constantly. And quantum tunneling is the reason why. Inside the nucleus, the alpha particle's wave function stretches toward the edge of the nuclear potential barrier. Even though it's unlikely, there's always a chance the particle will tunnel through. Over time, that small probability adds up, and eventually the particle pops out. That's radioactive decay in action. Without tunneling, many elements would never decay, and nuclear physics as we know it would grind to a halt. Tunneling is also critical for the most important energy source in the universe, nuclear fusion. In the cores of stars, hydrogen nuclei are crushed together under immense pressure and heat. But even with those extreme conditions, they don't really have enough energy to overcome the electrostatic repulsion between their positively charged protons. According to classical calculations, fusion shouldn't happen nearly as often as it does. Yet stars shine, and tunneling explains why. At those high temperatures, hydrogen nuclei get close enough for their wave functions to overlap. There's a tiny chance that one will tunnel through the repulsive barrier and fuse with another. Multiply that tiny chance by the unthinkable number of particles in a star, and you get a brilliant sustained fusion process. The furnace that powers everything from sunshine to supernovas. And it's not just distant stars that benefit from tunneling. We use it right here on Earth, in labs, in factories, even in experimental computers. One elegant example is the Scanning Tunneling Microscope, or STM. This device allows scientists to visualize surfaces at the level of individual atoms. It works by bringing an ultra-sharp tip extremely close to the surface of a material, just a few nanometers away. At that distance, electrons can tunnel between the tip and the surface. By measuring this tunneling current, the microscope builds up an incredibly detailed map of the atomic landscape. What's remarkable is that the STM doesn't touch the atoms it's imaging. It's relying entirely on tunneling, on the ability of electrons to slip quietly through empty space, across a gap, and into a detector. This non-contact technique gives scientists a way to peer into the quantum terrain with stunning precision. Tunneling is also at the heart of certain types of electronic components, like tunnel diodes and quantum dots, and it's a looming factor in the future of computing. As we shrink transistors to ever smaller sizes, we're running into quantum limits. At nanometer scales, electrons can tunnel through barriers that were once considered solid. It's as if the walls in our circuitry are starting to let particles sneak through when they're not supposed to. This presents both challenges and opportunities. On one hand, it creates noise and unpredictability in traditional electronics. On the other hand, it opens the door to quantum technologies that use tunneling rather than fight against it. At its core, tunneling teaches us something profound about the nature of reality. We often think of the world as made of hard boundaries. A particle can go here but not there. A wall is a wall. But the quantum world is more nuanced. Barriers are not impenetrable. They are probabilistic. They are suggestions, not absolutes. And while we might find that unsettling, it's also strangely elegant. Because of tunneling, particles are not confined to the straight paths we imagine. They can cheat, slip, blur through the cracks of logic. They remind us that the universe is not a machine made of perfect gears, but a shimmering tapestry of likelihoods and possibilities. The tennis ball still bounces off the wall, but the electron, the alpha particle, the photon, they might just glance at that same wall and say, "I think I'll take the shortcut." And somehow nature lets them. In everyday life, we think of nothing as, well, nothing. The absence of stuff. An empty room, a blank sheet of paper, the space under your bed where socks mysteriously disappear. And when we extend that idea to physics, we often picture the vacuum of space as a perfect void. A cold, silent expanse with absolutely nothing in it. But in quantum physics, nothing is never really empty. What we call the quantum vacuum is a restless, jittering stage. It's not filled with atoms or light or sound, but it's far from blank. Even when all particles have been removed and no fields are actively doing anything, the vacuum still seethes with energy. At the smallest scales, space is alive with invisible activity. Waves rising and falling, particles flickering in and out of existence. It's like the hum beneath silence, the glow behind darkness. And it all starts with uncertainty. Heisenberg's uncertainty principle doesn't just apply to particles' position and momentum, it also applies to energy and time. That means that even in a region of space where energy should be zero, the energy can briefly fluctuate. These fluctuations give rise to virtual particles which appear spontaneously, hang around for a fleeting moment, and then vanish as if they never existed. They're called virtual, not because they're imaginary, but because they can't be directly observed, only inferred through their effects. These quantum blips might seem like a mathematical curiosity, but they have very real consequences. One of the most striking examples is something called the Casimir effect. It's one of those rare phenomena that lets us see the quantum vacuum doing something tangible, something measurable. Here's how it works. Imagine placing two very thin, perfectly conducting metal plates extremely close together in a vacuum, just a few nanometers apart. According to classical physics, nothing should happen. There's no air between the plates, no forces acting on them, just an empty gap. But quantum mechanics says otherwise. Because the space between the plates is so small, only certain wavelengths of virtual particles can exist there. Ones that fit neatly between the boundaries. Outside the plates, however, there's no such restriction. The result, there's slightly more pressure from virtual particles outside the plates than between them, and this imbalance creates a force that pushes the plates together. That's the Casimir effect. It's a tiny force, but it's been measured. In precise laboratory experiments, scientists have observed these plates attracting each other exactly as quantum theory predicts. It's as if the vacuum itself is gently squeezing them, proving that even nothing has a kind of substance. This vacuum energy isn't just limited to quirky lab setups. It plays a role across the entire universe. In cosmology, there's the idea of vacuum energy density, the notion that the energy of empty space might be responsible for the accelerating expansion of the universe. We call this mysterious force dark energy, and while we don't fully understand it, the concept of a quantum vacuum buzzing with energy might be a big part of the puzzle. But there's a catch. The predicted energy of the quantum vacuum, according to quantum field theory, is enormous. If we tried to calculate the total vacuum energy of the universe using what we know from particle physics, we'd get a number that's wildly larger, like 120 orders of magnitude larger than what we actually observe. This is often called the worst prediction in physics, and no one has quite figured out how to fix it. But it highlights just how complex and surprising the vacuum really is. Back at the quantum scale, virtual particles also play a supporting role in other strange phenomena. In quantum electrodynamics, for instance, the interaction between charged particles is partly mediated by the constant exchange of virtual photons. These exchanges give rise to the electromagnetic force as we experience it. Even the mass of particles like protons is affected by the swarm of virtual quarks and gluons flickering around inside them. What we think of as stable, solid matter is really the result of constant interactions with this invisible, fluctuating vacuum. And while these particles appear and disappear faster than we can measure, their influence is everywhere. They slightly alter the energy levels of electrons in atoms. They contribute to the magnetic moment of particles, They're woven into the fabric of every interaction in nature. This might sound like science fiction, but it's been tested. When we correct our calculations to include vacuum fluctuations, like in the famous Lamb shift observed in hydrogen atoms, we find that the predictions match reality with breathtaking accuracy. The math is weird, the concepts are wild, but the results are solid. In a way, the quantum vacuum is the most fundamental field of all. Every other field, electromagnetic, gravitational, nuclear, exists within it. They ripple and hum against its background like instruments playing on top of a bass line that never stops. Some physicists even suspect that the vacuum holds clues to deeper truths. Could it be the source of all structure in the universe? Might it contain information about quantum gravity, or even about space-time itself? These are open questions, but one thing is clear. The vacuum is not a passive backdrop, it's active, it's structured, it's full of potential. Even in the coldest regions of space, where matter is scarce and starlight is a memory, the quantum vacuum is still there, vibrating, jittering, whispering the rules of existence to anything willing to listen. It's humbling to think that nothing is never truly nothing, that even in apparent stillness the universe teems with hidden activity. In the pauses between moments, in the gaps between particles, in the silence between stars, something is always happening. We live not on a quiet stage, but on one that murmurs beneath our feet. And while we may not hear it with our ears, physics has found the instruments to listen. The vacuum hums, the particles flicker, and reality dances to a rhythm we've only just begun to understand. In the quantum world, reality doesn't always behave like a story with a clear beginning, middle, and end. Particles don't just travel in straight lines. They drift in clouds of probability. They superpose, entangle, and sometimes tunnel their way through things that should be solid. But perhaps the most mysterious twist in this quantum tale comes when we ask a very human question. What happens when we look? This simple act of observing, of measuring, seems to trigger something dramatic, a shift, a change in the very nature of the quantum system. This is known as wave function collapse. Before measurement, a particle like an electron or a photon is described by its wave function, a mathematical object that holds all the possible outcomes of where it could be or how it might behave. That electron isn't in one place. It's in a blend of many possible places. Its spin isn't up or down, it's both. Its path isn't chosen, it's all of them at once. The wave function is a shimmering probabilistic fog. But then you measure it. You fire up your detector, you ask, where is it? And in that instant, the wave function collapses. The fog condenses. All those swirling possibilities snap into a single reality. The electron is suddenly there, in one precise spot. Its spin is up, or down, not both. And this collapse doesn't seem to happen gradually. It's not a slow fading of possibilities. It's abrupt, binary. One moment the system is in superposition, the next it's locked into a definite state. As if the universe, after much hesitation, makes a final decision the moment we check. That's weird enough on its own. But it gets weirder. Because no one knows exactly what causes the collapse. Is it the physical interaction with a measuring device? Is it the transfer of information? Is it consciousness? A camera? A fly buzzing past the lab? The truth is, the collapse of the wave function, though central to quantum theory, is not well understood. In fact, it might be the biggest mystery in all of modern physics. Different interpretations of quantum mechanics try to answer the question in different ways. The most traditional view is the Copenhagen interpretation, championed by Niels Bohr and Werner Heisenberg. In this view, the wave function is not a real physical object, it's just a tool for predicting probabilities. And collapse happens when a measurement is made, when we gain information. Before that, asking about what's really happening isn't meaningful. The electron isn't somewhere waiting to be found. It simply isn't anywhere in particular until we look. It's a practical approach. It makes the math work. But it leaves many scientists unsatisfied, because it doesn't really explain what measurement is, or why the wave function must collapse at all. Then there's the many worlds interpretation, which throws collapse out the window entirely. According to this idea, the wave function never collapses. Instead, every possible outcome happens, just not in your universe. Measure an electron spin and the universe splits. In one version, it's spin up. In another, spin down. You only experience one of those outcomes, but the others still exist, unfolding in parallel. No collapse, no mystery, just branching realities. It's a bold idea, and surprisingly consistent with quantum math, but it comes at the cost of multiplying universes like cosmic confetti. Every measurement, every interaction, every choice, a never-ending spray of realities. It's elegant in one sense, absurd in another. Other interpretations aim to make collapse feel more real. In the objective collapse theories, the wave function is a physical thing that collapses spontaneously, randomly, without measurement. It's just that measurement increases the chance of collapse. These theories introduce new rules or even new physics to explain when and how collapse happens. They're still being tested, but they offer an intriguing possibility that wave function collapse might be something nature does, not just something we see. Then there's cubism, a more recent and radical view. It suggests that the wave function doesn't describe the system at all. It describes our beliefs about the system. It's a personal, subjective tool for predicting outcomes. And collapse isn't a physical event, but a mental update. Like learning a new fact and revising your expectations. Reality doesn't change. You do. Some physicists find that refreshing. Others find it deeply unsatisfying. After all, shouldn't physics be about the universe, not our opinions? There's also the role of decoherence, which doesn't explain collapse directly, but helps describe how superpositions seem to vanish in large systems. When a quantum system interacts with its environment, even just a few stray photons, it becomes entangled with the world around it. That entanglement causes the interference patterns we associate with superpositions to disappear. To us, the system looks like it collapsed, even though it hasn't truly picked a state. Decoherence explains why cats don't stay both alive and dead, but it stops short of saying how one outcome becomes real. And there we sit. More than a century after the birth of quantum theory, wave function collapse remains a ghost in the machine. The math works brilliantly. We can predict outcomes with incredible precision. But what exactly collapses? When? Why? Is collapse even real? Or are we just seeing the limits of our own understanding? There's no shortage of ideas. Some researchers believe we need a new theory of measurement, or a deeper theory of reality that goes beyond quantum mechanics. Others are content with the ambiguity. They say the predictions work and the rest is philosophy. But philosophy matters, especially here. Because the question of wave function collapse isn't just about particles. It's about what the universe is. Is reality fundamentally probabilistic? Is it observer-dependent? Is it constantly branching? Is it shaped by information, by consciousness, by something we've yet to discover? And how much can we ever really know? You can think of collapse as the moment the quantum world tips into the classical, a kind of phase change, like water freezing into ice. But unlike water, the rules of this transformation are murky. We don't know the temperature, we don't know the pressure. We just know that at some point the fog becomes a shape, and possibility becomes presence. It's easy to get lost in the metaphors. Is the wave function a veil, a dream, a menu of futures waiting to be chosen? Perhaps it's all of those, and none. Perhaps what collapses is not the wave function itself, but our illusion that the world must always be definite, always be one thing or another. Maybe the universe is content being undecided. Maybe we're the ones who insist on conclusions. What happens when we measure? Maybe the better question is, what do we think happens? And are we prepared for the answer to be stranger than we hoped, but truer than we imagined? If quantum physics had a hometown, it would probably be Copenhagen. Not because of the scenery, though Denmark does have a charming supply of windmills and bicycles, but because it's where some of the strangest ideas in physics were first seriously discussed, argued over, and quietly accepted. At the heart of this story is Niels Bohr, a Danish physicist with a gentle demeanour and a taste for long, complex sentences. Bohr helped shape one of the most influential views of quantum mechanics, a perspective that came to be known as the Copenhagen interpretation. The idea is deceptively simple, in fact that's part of its charm. According to the Copenhagen view, quantum systems don't have definite properties until they're measured. An electron doesn't have a fixed position. A photon doesn't commit to a particular polarization. A particle doesn't choose a state until an observation forces it to. Before measurement, reality is a fuzzy cloud of possibilities, a probability wave. Measurement doesn't just reveal something that was already there, it creates the outcome. In other words, reality isn't quite real until we ask it to be. That's a bold statement, and it's the kind of thing that makes philosophers sit up and physicists reach for coffee. But Bohr and his colleagues weren't trying to make the universe mysterious for the sake of it. They were trying to make sense of experimental results. Every time they tried to treat particles like little billiard balls, the math fell apart. But when they treated particles as probability waves that only resolve upon measurement, things clicked into place. The wave function, in this view, isn't a physical thing. It doesn't describe a particle's actual position or momentum. Instead, it encodes everything we can know about the system. It's a mathematical catalogue of possibilities, not a map of what is. This leads to one of the Copenhagen interpretation's central claims. Questions about a system's state before measurement are meaningless. Asking where the electron was before you measured it doesn't make sense, because where only becomes a meaningful concept after the measurement. Reality is not something you peel back like a curtain. It's something that snaps into focus the moment you look. It's not that the particle was hiding its true nature. It simply didn't have one yet. Understandably, not everyone found this satisfying. Albert Einstein, for one, was famously uneasy with the idea. He wanted a universe that existed independently of whether anyone was observing it. He believed in an underlying reality, objective and deterministic, even if it was currently hidden from view. To Einstein, the Copenhagen interpretation sounded like saying the moon doesn't exist unless you're looking at it. Bohr disagreed, but he didn't try to offer a grand metaphysical solution. Instead, he embraced a kind of pragmatic ambiguity. His position was that quantum theory tells us what we can say about nature, not necessarily what nature is. The role of science, in this view, isn't to discover what's really out there, but to describe the outcomes of experiments as precisely as possible. If that sounds a little unsatisfying, you're not alone. The Copenhagen interpretation is often accused of being more of a prescription than a description. It tells you how to use the equations, it tells you what the outcomes will be, but it doesn't tell you what's actually going on behind the scenes. This gave rise to the now infamous phrase, "shut up and calculate." It's not a quote from Bohr himself, but it captures the mood of many working physicists. The idea is, stop worrying about the metaphysical implications and just use the theory. It works. It gives correct predictions. Isn't that enough? And to be fair, the Copenhagen approach does work. It's the default interpretation used in countless textbooks, labs, and classrooms. It underpins the design of semiconductors, lasers, and quantum computers. It has never failed an experimental test. For many scientists, that track record outweighs any philosophical discomfort. But still, the discomfort lingers. If reality only becomes real when measured, what does that say about the universe before observers existed? Did nothing have definite properties before conscious life arrived? Was the early universe in a kind of suspended animation, waiting for someone to look? Most physicists would say no. The Copenhagen interpretation doesn't require a conscious observer, just an interaction with a measuring device, or with the environment. Observation, in this context, is just a process of extracting information from a quantum system in a way that forces it to pick a side. But even this leads to more questions. What counts as a measurement? At what point does the wave function collapse? Why does the universe follow this strange rule at all? The Copenhagen camp tends to answer with a shrug and a smile. The theory doesn't explain why collapse happens, it just says when. If you want a deeper explanation, you'll need to look elsewhere, and many have. Competing interpretations like many worlds, pilot wave theory, and objective collapse models all aim to offer a more complete picture. Each tries to preserve some classical intuition, that reality exists independently, that cause leads to effect, that observation doesn't get special treatment. But each of these alternatives comes with its own complications. Copenhagen, by contrast, is lean. It doesn't introduce hidden variables, it doesn't multiply universes, it just lays out a set of rules. Calculate the wave function, apply the measurement postulate, and predict the outcome. Simple, direct, effective. Maybe that's its appeal. In a field full of strange possibilities, the Copenhagen interpretation offers a kind of calm. It's not trying to solve every mystery. It's content to describe the world we can see, measure, and interact with, without claiming to know the deeper machinery behind the curtain, and maybe that's enough. Bohr often spoke in layered, almost poetic language. He once said, "Those who are not shocked when they first come across quantum theory cannot possibly have understood it." He understood that the Copenhagen approach wasn't about making peace with reality, it was about making peace with uncertainty. Quantum mechanics is weird, but rather than wrestle it into something tidy, the Copenhagen interpretation invites us to accept that weirdness and to work within it, without demanding that the universe explain itself. It's not a final answer, it's a quiet rulebook, a reminder that in the quantum world, simplicity and discomfort often travel together, and that sometimes the best we can do is shut up and calculate. Imagine you're holding a coin between your fingers. You flip it. It spins through the air, gleaming in the light, and lands with a soft clink. Heads. But according to one interpretation of quantum mechanics, something else happened too. Somewhere, not here but still real, the same coin landed tails, and somewhere else again, it landed on its edge, rolled off the table, and landed under the couch. Every possible outcome of that flip unfolded, not as a maybe, not as a probability, but as a real branch of reality. And you just happen to find yourself in the one that saw heads. This is the strange and elegant idea behind the many worlds interpretation of quantum physics. It began as a thought experiment, an alternative way of looking at the infamous wave function collapse problem. You may remember the wave function, the mathematical cloud of probabilities that defines everything about a quantum system. In the traditional Copenhagen view, when you make a measurement, the wave function collapses, and one possibility becomes real. But what if it never collapses at all? In 1957, physicist Hugh Everett III proposed a radical idea. Maybe the wave function is always evolving smoothly and deterministically. Maybe, when you measure a system, you don't force it to choose a single outcome. Instead, you split. The universe splits. Every possible outcome plays out, but each in its own separate branch of reality. It sounds dramatic, like something from science fiction, but Everett wasn't writing a novel, he was doing math. And his version of quantum mechanics is mathematically identical to the standard version, just without the extra rule that says collapse happens when you observe. In his view, the wave function never collapses, it only branches. Here's how it works. Imagine an electron with two possible spin states, up and down. If you measure its spin, classical quantum mechanics says the electron is in a superposition of both states until measured, at which point it chooses one. Everett says no choosing necessary. Instead, the measurement causes the system and the observer to split into two correlated branches. In one, you observe spin up, in the other, spin down. Both outcomes are real. Both versions of you exist, each in a different branch of the universe. No randomness, no collapse, just a growing, branching tree of reality. This may sound like a recipe for science fiction overload. Parallel universes, doppelgangers, infinite copies of everything. But the many worlds interpretation doesn't rely on fantasy. It doesn't propose new physics or untested forces. In fact, its central appeal is that it sticks only to the mathematics we already use. It simply refuses to add the extra assumption that something magical happens when you look. To supporters of many worlds, this is its strength. The idea is weird, but the math is clean. Of course, not everyone is comfortable with this. For one thing, if the universe is constantly branching into new realities, where do all these universes go? Are they stacked on top of each other? Floating in some higher dimensional multiverse? The theory doesn't say, and that's part of the philosophical tension. Many worlds isn't a theory about the structure of space. It's a statement about how quantum systems evolve. The other branches are real, but they don't interact with ours. Once a split occurs, the branches decohere, meaning they no longer interfere with each other. They become, for all practical purposes, invisible. That makes the theory hard to test directly. After all, if we can't observe the other branches, how do we know they're there? That's the central criticism. Many worlds may be elegant, but is it falsifiable? Can you prove it wrong? Supporters argue that's the wrong question. They say it's not about adding new predictions. It's about not adding unnecessary assumptions. If the wave function evolves smoothly according to the Schrödinger equation, and that equation never includes collapse, then why assume collapse exists at all? Occam's razor, often paraphrased as the simplest explanation is usually the right one, cuts both ways here. Copenhagen keeps the universe small by adding collapse. Many worlds keeps the math simple by accepting a very large universe. But is that universe too large? Let's take a calming moment to imagine the scale. Every time a quantum interaction has multiple possible outcomes, the universe branches. That includes not just lab experiments, but molecular collisions, radioactive decays, photon emissions, and everything else. The universe isn't splitting every now and then, it's branching constantly, exponentially, unimaginably. But in the same way, we don't feel the Earth spinning under our feet. We don't feel the branching. To us, it's invisible, seamless. We simply see one outcome, as if that's all there ever was. It's also important to say that in many worlds, these other realities aren't parallel lives in the sci-fi sense. You're not hopping between them. You don't get to meet your other selves. Each branch is causally isolated from the others. There's no communication across the divide, no peeking at other versions of yourself eating soup instead of salad. Once a split happens, it's permanent. This avoids a lot of the philosophical headaches that come with wave function collapse. There's no need to define what counts as a measurement, or when reality becomes real. Everything evolves smoothly. Measurement is just entanglement. You and the system become linked, and the world unfolds accordingly. But that calm elegance also comes at a cost. If every possible outcome happens, then why do we feel like only one outcome occurred? Why does it feel like the coin landed heads and not tails? If all outcomes are real, what does probability even mean? Many worlds redefines probability not as the chance that something will happen, but as a measure of how much you ends up in each branch. It's a subtle shift. Instead of asking, "What are the odds?" you ask, "What fraction of my future selves see this result?" It's not intuitive, but neither is quantum mechanics in general. And despite all its strangeness, many worlds has inspired deep, serious research. Some physicists believe it could help unify quantum mechanics with gravity. Others see it as a foundation for understanding quantum computing, where superpositions and entanglements do computational heavy lifting across possible states. It also offers a unique kind of comfort, or disquiet, depending on your perspective. In this interpretation, no outcome is ever truly lost. Every possibility exists somewhere. The decisions you didn't make, the chances you didn't take, they're all still out there, playing out in parallel timelines, not just hypotheticals, but real, physical events in real, physical worlds. It's not meant to make you feel small. If anything, it's a reminder that the universe may be more generous than we imagined. Not just a single story unfolding, but a vast and shimmering library with every possibility inked into existence. So when you think of many worlds, don't picture a noisy stack of cartoon realities. Picture a quiet, branching tree, each twig a path, each leaf a world, each outcome a poem written in the language of physics, and all of them in their own way true. Imagine pulling back the curtain on everything. The stars, the oceans, your chair, your hand, even the light falling gently on your pillow. What if all of it, all matter and energy, wasn't made of solid things at all? What if the most fundamental stuff of reality wasn't stuff at all but vibrations? Waves, invisible ripples spreading through fields that fill all of space. Welcome to the quiet but profound world of quantum field theory, where the universe is not built out of particles, but out of fields that shimmer beneath everything. Let's start gently. In classical physics, a field is something that assigns a value to every point in space. A familiar example is the electric field, an invisible force that tells a charged particle how it should move. If you put a positive charge into an electric field, it feels a push. That's the field at work. Fields are smooth, continuous, and fill the universe like invisible jelly. Now quantum mechanics comes along and sprinkles uncertainty onto the picture. It says fields don't just sit there quietly. They fluctuate. They buzz, even in the absence of any real particles. Every field, electric, magnetic, gravitational, is quantum in nature. It jiggles, even when it seems empty. Even the vacuum, as it turns out, isn't truly calm. It's restless. And here's the leap. In quantum field theory, or QFT, everything is a field. Every particle you've ever heard of, electrons, photons, quarks, neutrinos, is just a little blip in its corresponding field. A particle is not a tiny marble flying through space. It's a localized ripple, a bump, a wiggle in an underlying field that fills all of reality. Let's take the electron. Somewhere out there in space is the electron field, a quantum field that exists everywhere. When you see an electron, you're not looking at a separate self-contained object. You're observing a specific quantized excitation of that field. The field got excited in a localized way, and that's what you call an electron. Same goes for photons. The electromagnetic field fills all of space. When a light particle zips by, it's not a little bullet. It's a ripple, a tiny vibration in the electromagnetic field. Turn the knob on that ripple just right, and you get visible light. Turn it differently, and you get microwaves, or X-rays. But it's all just modes of dancing in the same field. There's a field for every known particle. Quark fields, gluon fields, Higgs fields. Even the elusive graviton, if it exists, would be a ripple in the gravitational field. So where did our old friend the particle go? In a sense, particles are a useful fiction, a way to describe the behavior of fields in certain contexts. When the field is localized and the ripple behaves as a discrete packet of energy, it's convenient to call it a particle. But that's just our label for a behavior. The field is fundamental. The ripple is what we see, but the field is what's really there. This shift in perspective is profound. It turns the universe from a Lego set made of tiny blocks into something more like a symphony, an infinite orchestra of overlapping notes, with reality emerging from their interference and harmony. Quantum field theory also explains some puzzling features of quantum mechanics that standard quantum theory struggles with. For instance, how do particles create and destroy themselves in high-energy reactions? Simple, they're just field excitations. Smash enough energy into a region of space, and you can jiggle a field hard enough to spawn a new ripple. That's how particle collisions in places like CERN can produce entirely new particles out of what seems like thin air. And what about antiparticles? The electron's shadowy twin, the positron. In quantum field theory, antiparticles are just another mode of excitation in the same field, with opposite properties. Nothing spooky, just more symmetries in the rippling. Here's a particularly elegant twist. Forces themselves are mediated by fields. The electromagnetic force, it's the result of charged particles exchanging photons, ripples in the electromagnetic field. The strong force, it's gluons, vibrating in the gluon field, binding quarks together. Gravity, if it's ever successfully quantized, would involve tiny ripples in the gravitational field. Gravitons. Even empty space isn't really empty. Quantum field theory predicts that fields are never completely still. They're always jittering with vacuum fluctuations. These fluctuations can have measurable effects, like the Casimir effect, where two metal plates placed very close together in a vacuum feel a force pulling them together, caused by changes in the field's energy between them. There's something wonderfully serene about this picture. The idea that space itself is not a passive backdrop but an active participant. Every point in space is alive with potential. Every particle, every interaction, every beam of light or burst of energy is just the field expressing itself. Of course, quantum field theory is complicated. It's not something you can casually calculate on a napkin, unless your napkin is the size of a blackboard and your chalk is labelled Feynman diagrams. But the conceptual takeaway is elegant. Nature at its most fundamental is not made of things. It's made of excitations, patterns, energy arranged in space and time. Even mass, the stubborn weighty quality of matter, is, in many cases, an emergent feature of field interactions. The Higgs field, discovered experimentally in 2012, is responsible for giving many particles their mass. Particles interact with this field like swimmers moving through molasses. The more resistance they feel, the more mass they appear to have. So here we are, nestled in a world of fields. You, as you listen to this, are a delicate pattern in the electron field, the quark field, the photon field. Your thoughts are patterns of excitation. The very atoms of your body are nodes in a cosmic meshwork of fields, humming in invisible harmony. You don't end at your skin. The fields that define you spill out into the universe. There is no sharp edge, no hard boundary, just softer or stronger ripples, fading into the broader sea of quantum reality. Quantum field theory doesn't just describe the universe, it is the universe, or at least it's the best map we've drawn so far. A map where reality is not made of things bumping into each other, but of fields interwoven in a dance too fast, too subtle, and too beautiful to ever fully catch. And if you're still awake, you might be wondering, if everything is a ripple in a field, what are we rippling through? That, dear listener, is a question for another dream. If the universe came with a cookbook, the standard model of particle physics would be its ingredient list, minus a few mystery spices like dark matter and dark energy. It's a surprisingly compact recipe, elegant in its organisation and just a little bit chaotic in its naming conventions. But for all its quirks, this model is one of the most successful theories in the history of science. It tells us what the universe is made of, how those parts interact, and why reality looks and behaves the way it does. Let's start by introducing the cast. At its heart, the standard model is a collection of elementary particles. Particles that, as far as we can tell, cannot be broken down into anything smaller. You can think of them as the fundamental building blocks of matter and force, woven together by the threads of quantum fields. There are three broad families: quarks, leptons, and bosons. Quarks are the stuff of protons and neutrons, the solid core of atoms. There are 6 types, or flavours, of quarks: up, down, charm, strange, top, and bottom. Yes, those are their actual names. Physicists can do the most precise math imaginable, but naming things, that's where the chaos blooms. The up and down quarks are the lightest and most common. A proton is made of 2 ups and 1 down, a neutron is made of 2 downs and 1 up. That means everything you see, touch, or are is mostly up and down quarks, plus electrons, which we'll meet in a moment. The other quarks, charm, strange, top and bottom, are heavier, rarer, and mostly show up in high-energy environments like particle accelerators or cosmic rays. They're like the special guest stars of the particle world. Flashy, short-lived but important in the grand scheme. Next we have the leptons. This group includes the electron, which you've met many times before, buzzing around atoms, carrying electricity, and generally making life possible. Electrons also have cousins. There's the muon, which is like a heavy electron, and the tau, which is even heavier still. Like the exotic quarks, these heavier leptons don't last long in the wild, but they show up in high-energy reactions and leave distinct traces. Each of these charged leptons comes with a neutral partner, the neutrino. There are 3 of them, 1 for each flavour, and they're incredibly light, incredibly fast, and incredibly aloof. Neutrinos barely interact with matter at all. Billions pass through your body every second without leaving a trace. They're the introverts of the universe, always present, rarely noticed. So far we have 6 quarks and 6 leptons, arranged in 3 neat generations. That's 12 matter particles total, all dancing on a stage set by quantum fields. But matter alone doesn't make a universe. We need forces, the rules that govern how these particles interact. That's where the bosons come in. Bosons are the force carriers. Each fundamental force has its own messenger particle, a kind of quantum handshake that tells other particles what to do. For the electromagnetic force, the carrier is the photon, the particle of light. It's massless, it moves at the speed of light, and it keeps electrons bound to atoms. Without photons, chemistry and breakfast wouldn't exist. The weak nuclear force, responsible for processes like radioactive decay, has 3 bosons, the W+, W-, and Z bosons. Unlike the photon, these are heavy. So heavy, in fact, that they're only involved in interactions at very short ranges. They help turn neutrons into protons and vice versa, fueling the fusion that powers stars. Then there's the strong nuclear force, the glue that holds quarks together inside protons and neutrons, and binds those protons and neutrons inside atomic nuclei. Its carrier particle is the gluon, a massless but energetic force bearer that comes in 8 varieties. Gluons are like a very excitable group of toddlers in a ball pit, constantly exchanging energy, never sitting still, and entirely responsible for why your atoms don't fall apart. Finally, there's the newcomer, the Higgs boson. This particle was confirmed experimentally in 2012 at CERN and earned a Nobel Prize the following year. The Higgs boson is the manifestation of the Higgs field, which permeates space and gives mass to many of the other particles. Without the Higgs mechanism, the standard model would describe a very strange world, one where most particles zipped around massless, unable to clump together into atoms. So to recap, we have 12 matter particles, 6 quarks and 6 leptons, and 5 force-carrying bosons, photon, W, Z, gluon, and Higgs. All of this is the standard model, and it works beautifully. This model has predicted the outcomes of countless experiments with astonishing precision. From the behavior of particles in colliders to the decay rates of radioactive isotopes, the standard model just keeps being right. It's not perfect, but it's remarkably stubbornly good at what it does. Of course, it has a few holes. For one, it doesn't include gravity. The standard model is a quantum theory, while gravity is best described by Einstein's general relativity, a classical theory. Merging these 2 frameworks is one of the biggest unsolved problems in physics. Then there's dark matter. Astronomical observations suggest that most of the matter in the universe is invisible and doesn't interact with light. The standard model doesn't account for it. None of its particles can explain the gravitational effects we observe in galaxies. And let's not forget dark energy, the mysterious force driving the universe's accelerating expansion. That too is outside the standard model's jurisdiction. In fact, the standard model describes only about 5% of the universe. But what a 5% it is! Every atom, every interaction, every burst of light, every breath you take, it's all contained within this shimmering lattice of particles and forces. It's often said that the standard model is complete but unsatisfying. It's like finishing a puzzle only to realize the image on the box was just a small section of a much larger picture. But still, what's there is stunning. Elegant symmetries, intricate relationships, and mathematical structures that link particles in ways that hint at a deeper unity. Some theorists suspect that all of this, quarks, leptons, bosons, may someday be unified under a grand unified theory, or even a theory of everything. These dreams may lie beyond the reach of current experiments, but they're guided by the same spirit that built the Standard Model, the belief that nature is knowable, that patterns lie beneath the chaos, and that even the wildest forces obey quiet laws. So the next time someone asks what the universe is made of, you can smile and say, mostly quarks, a few leptons, and a handful of bosons. And then, for fun, you can add, oh, and don't forget the Higgs field. Without it, none of this would have any weight. It's not the full story, but it's a pretty good opening chapter. At the intersection of dazzling complexity and mathematical perfection sits a theory that might just be the crown jewel of physics, quantum electrodynamics, or QED for short. It's the framework that explains how light and matter interact, and it does so with such precision that even the pickiest decimal places stand in awe. At its core, QED describes the quantum dance between electrons and photons. Every flicker of light, every spark, every push and pull between charged particles. It's all a performance choreographed by the rules of QED, and somehow, despite involving an infinite number of possible interactions and mind-bending probabilities, the final answers it gives match experiments with ridiculous accuracy. We're talking about predictions confirmed to better than 1 part in a billion. That's like measuring the width of North America to within the thickness of a human hair, and being right. So how does QED manage this? Let's start with the problem it solves. In the early 20th century, physicists knew that electrons interacted with the electromagnetic field. When an electron accelerates, it emits light. When it absorbs light, it changes energy levels. But calculating the exact behavior of these interactions at the quantum level turned out to be a nightmare. The equations blew up. Infinities appeared where they shouldn't. You try to work out how an electron emits a photon, and the math would spit out nonsense like infinite energy, which is not helpful unless you're trying to cook the entire universe. Enter a physicist with an impish grin and a love for bongo drums, Richard Feynman. Feynman, along with Julian Schwinger and Shinichiro Tominaga, found a way to make QED behave. But Feynman went one step further. He made it visual. He invented Feynman diagrams, a graphical way to represent particle interactions that turned complicated quantum calculations into almost childlike scribbles. In these diagrams, particles are lines. Time flows from left to right. An electron might enter from one side, emit a photon, and then continue on its way. That photon might zip off and hit another electron, or loop back around and affect the same one. Each of these paths has a mathematical expression, and QED tells you to add them all up. Not just the most likely one, but every possible way the interaction could happen. That includes some pretty wild possibilities. An electron emits a photon, which becomes an electron-positron pair, which then annihilates and becomes another photon, which is absorbed again. These are known as virtual particles. They exist only in the mathematical interludes between real, measurable events, but they shape the outcome in very real ways. This is where QED becomes less like physics and more like poetry written in calculus. It doesn't just account for what does happen, it accounts for everything that could happen. Every zig, every zag, every loop and squiggle is part of the final answer. And somehow, when all of those possibilities are woven together, the result is a prediction so precise it could tell you how an electron would behave on the far side of the galaxy, down to the tiniest decimal. One of the triumphs of QED is its explanation of the anomalous magnetic moment of the electron. The electron has a tiny magnetic field, like a miniature bar magnet. Classical physics predicts its strength, but quantum effects tweak it just a little. QED calculates this tweak and matches the experimental result to over 10 decimal places. It's not just good, it's stunning. The theory also elegantly explains phenomena like Compton scattering, where a photon bounces off an electron. Bremsstrahlung, where a particle emits radiation when slowing down, and pair production, where light can transform into matter and antimatter. All of these processes, which sound like sci-fi spells, fall naturally out of the QED framework. It's worth mentioning that QED doesn't stand alone. It's the quantum field theory that describes electromagnetism, but it's also the prototype for other quantum field theories. The strong force has its own version called quantum chromodynamics. The weak force is handled by electroweak theory, which unifies electromagnetism and the weak interaction. But QED came first and it set the standard. And here's something charming. Despite its mind-melting math, QED is deeply intuitive once you get the hang of it. Feynman himself often said that the rules of quantum electrodynamics could be written on the back of a napkin. In his signature style, he boiled it down to this: particles take every possible path, each with a probability amplitude. You square the sum to find the actual probability, and that's it. The rest is just bookkeeping. This idea that nature explores every path is at the heart of the quantum worldview. An electron doesn't just go from point A to point B, it takes every route, through every obstacle, around every tree, and under every bridge, all at once. The universe is calculating all of those possibilities, and QED is how we peek into that process. It's also a testament to how weird quantum physics can be without breaking down. You might think, surely a theory this strange must have limits. And you'd be right. QED doesn't include gravity, and it doesn't explain dark matter. But within its domain, it reigns supreme. It is quite simply the most accurately tested theory in the history of science. Even Feynman, who was famously skeptical of excessive admiration, admitted that QED was extraordinary. But he also warned us not to get too comfortable. Nature, he liked to say, always has more up her sleeve, and while QED might be the best theory we have, it may not be the best theory we can have. Still, for now, it's a masterpiece. A theory that began in tangled math and philosophical frustration, and emerged as a clear, precise description of the quantum heartbeat of the universe. Light and matter interacting in an eternal whisper, described with such grace that even the decimals seem impressed. And in that whisper lies the light from distant stars, the pulse of your smartphone screen, and the gentle glow of a bedside lamp, all choreographed by a theory so subtle you barely notice it working, but it's there, in every flicker, every reflection, every breath of illumination. Quantum electrodynamics, a quiet triumph, a dance written in fields and photons, performed billions of times per second, and always, without fail, on cue. If classical computers are like carefully trained librarians, efficient, orderly, and great at flipping through books one page at a time, then quantum computers are more like very strange poets who read all the books at once in overlapping whispers and somehow still find the answer. It sounds like magic, and in some ways, it feels like it. But quantum computing is real, and it's built on the same bizarre principles that make up the heart of quantum physics. To understand what makes a quantum computer different, you first need to meet the bit's weirder cousin, the qubit. In a classical computer, everything boils down to bits. A bit is a binary unit of information. It can be either 0 or 1, like a switch that's off or on. These bits are the building blocks of everything your computer does, from streaming videos to calculating your taxes, and classical computers are great at manipulating lots of bits very quickly. But a qubit, short for quantum bit, doesn't just live in a state of 0 or 1. Thanks to the magic of superposition, a qubit can be in a blend of both states at once. Imagine a spinning coin that's neither heads nor tails, until you stop it and observe the result. While it's spinning, it contains the potential for both outcomes. This means that a single qubit holds more than one state simultaneously, and as you add more qubits, the power of that superposition grows exponentially. 2 qubits can hold 4 possible combinations, 3 qubits hold 8, 20 qubits? Over 1 million. With enough qubits, a quantum computer could, in theory, explore an astronomical number of possibilities in parallel. That's the key idea behind quantum computing: parallelism. While a classical computer tests each path one by one, a quantum computer explores many paths at once, though not in a way that gives you all the answers instantly. The trick lies in manipulating the system so that, when measured, the right answer is the most likely to appear. It's not brute force guessing, it's more like shaping the probability landscape so the correct solution rises to the top. But there's another quantum trick up its sleeve: entanglement. When qubits become entangled, the state of one is linked to the state of another, even across distances. This allows for complex correlations between qubits that classical bits simply can't replicate. It's like a dance between particles. If one twirls, the other twirls too, no matter how far apart they are. This entanglement allows quantum computers to perform operations that would take classical machines vast amounts of time and energy. For certain problems, like simulating molecules or factoring large numbers, quantum approaches promise enormous speed-ups. But now comes the part where we slow down and breathe a little. Quantum computers are not going to replace your laptop anytime soon. They are specialized tools, not general-purpose devices. For tasks like browsing the web or editing a video, your classical computer remains the reigning champion. In fact, building and running a quantum computer is hard. Qubits are incredibly delicate. They can be disrupted by tiny vibrations, fluctuations in temperature, even stray magnetic fields. Maintaining a qubit's coherence, its ability to stay in superposition and entanglement, requires extreme care. Many systems must be cooled to temperatures near absolute zero. That's colder than deep space. And then there's error correction. In classical computers, if a bit flips unexpectedly, it's fairly easy to detect and fix. In quantum systems, it's much trickier. You can't simply copy a qubit state without disturbing it, thanks to the no-cloning theorem. So researchers have had to invent clever schemes using many physical qubits to protect one logical qubit. It's like wrapping your whispering poet in layers of soundproof insulation, so they can keep reciting without interference. Despite these challenges, progress has been impressive. Companies and research labs have built quantum computers with tens to hundreds of qubits. Some have demonstrated quantum supremacy, performing tasks that would take a classical computer an impractical amount of time. Others are developing systems known as NISQ devices, short for Noisy Intermediate Scale Quantum, which explore what we can do with imperfect but still useful quantum machines, and there are real-world applications being explored. One promising field is quantum chemistry. Simulating the behavior of molecules at the quantum level is incredibly difficult for classical computers, but quantum machines are naturally suited for it. This could revolutionize materials science, drug discovery, and even battery technology. Another exciting area is optimization. Solving problems with many competing variables, like finding the best delivery routes or allocating resources efficiently. Quantum algorithms may be able to find solutions faster and with fewer steps than traditional methods. And then there's cryptography. Some quantum algorithms, like Shor's algorithm, could one day break widely used encryption methods by factoring large numbers incredibly fast. This has sparked a new branch of security known as post-quantum cryptography, where researchers are designing encryption schemes that even quantum computers can't crack. Still, we're in the early days. Most quantum computers today are noisy, fragile, and limited in what they can do. The dream of a fault-tolerant large-scale quantum computer is still years, if not decades, away. But that doesn't make the journey any less fascinating. What's particularly delightful is how quantum computing takes the strangest parts of quantum mechanics, the parts that once seemed like philosophical puzzles, and turns them into tools. Superposition, once a curiosity, becomes a resource. Entanglement, once spooky, becomes useful. Even measurement, that act of collapsing possibilities into a single outcome, becomes a step in the calculation. It's almost poetic. The very weirdness that made quantum theory so unsettling is now being harnessed to solve problems that were once thought impossible. It's like taming a wild wind, not by fighting it, but by sailing with it. Quantum computers invite us to rethink what it means to compute. They challenge the boundaries between certainty and probability, between logic and fuzziness. They remind us that beneath the surface of classical reality lies a much stranger landscape, one where information is soft and tangled, and answers emerge not from single steps, but from orchestrated patterns of possibility. We may not know exactly where this quantum path will lead, but the journey itself, quiet, intricate, full of potential, is already rewriting our understanding of what machines and minds can do. In the world of quantum physics, we expect things to be strange. Subatomic particles teleport through barriers, spin in two directions at once, and form entangled pairs that whisper across the cosmos. But there's a place we usually don't expect to see quantum behavior: biology. Biology is messy, warm, and wet. It operates in a noisy world full of jiggling molecules, random collisions, and fluctuating energy. Quantum effects, on the other hand, are notoriously fragile. They're easily disrupted by heat and chaos. That's why we build quantum computers in freezing cold labs and isolate particles in high vacuum chambers. And yet somehow life seems to be using quantum tricks of its own. Take the robin, for example, a small unassuming bird with a surprising sense of direction. Robins are migratory, flying thousands of miles with uncanny precision. But what's guiding them? How do they know which way is north? Scientists long suspected that birds had a built-in compass, but the details of how it worked remained elusive. Then came the radical idea: quantum entanglement might be involved. The hypothesis goes something like this. Inside a bird's eye there may be a protein, likely called cryptochrome, that contains a pair of entangled electrons. When light hits the molecule, it excites these electrons, causing them to become quantum linked. Their entangled spins then interact with Earth's magnetic field, influencing a chemical reaction in a way that depends on the direction the bird is facing. If that sounds like science fiction, you're not alone. The idea was met with skepticism. Entanglement is delicate. Could it really survive inside a living cell, among churning proteins and bustling water molecules? Surprisingly, early experiments suggest it might. There's growing evidence that birds really do rely on a quantum process to detect magnetic fields. It's not yet fully proven, but the signs are promising. If true, it means nature has figured out how to preserve quantum information in a biological setting, a feat human engineers are still struggling to perfect. Now let's shift gears to something green and leafy. Plants, like birds, are masters of a subtle quantum game. Consider photosynthesis, the process by which plants turn sunlight into chemical energy. It sounds simple enough. Light hits a chlorophyll molecule, which absorbs the energy and transfers it to a reaction center where it's stored. But how does that energy get there so efficiently? You might think it hops randomly from molecule to molecule until it reaches the right spot. That would be a slow and clumsy method. But measurement suggests something far more elegant is happening. The energy appears to explore multiple paths simultaneously, as though the system is using quantum coherence to find the most efficient route. Imagine dropping a marble onto a maze, and instead of rolling down one corridor, it spreads out like a wave, feeling every possible path, then settling on the shortest. That's how some researchers believe photosynthetic complexes behave. The energy doesn't wander aimlessly. It takes the best route thanks to a bit of quantum navigation. This is astonishing because these systems are warm, biological and noisy. Yet quantum coherence seems to persist long enough, sometimes on the scale of picoseconds, which in the world of molecules is a decent stretch of time, to influence outcomes. If plants are quantum strategists, it raises a tantalizing possibility. Has evolution learned to harness quantum mechanics? There's no reason to think biology can't make use of the same principles we find in physics labs. After all, nature had billions of years to experiment, and organisms that found clever quantum shortcuts, whether for energy efficiency, navigation or sensing, may have enjoyed a survival advantage. Speaking of sensing, there's one more biological mystery that might have a quantum answer: the sense of smell. We usually imagine that smell works by shape. A molecule fits into a receptor in your nose like a key fitting into a lock, and voila, you detect the scent. But that theory has some holes. Molecules with similar shapes can smell wildly different, and some molecules with different shapes can smell exactly the same. One alternative idea is the vibrational theory of olfaction, which suggests that our noses don't just detect shape, they detect how molecules vibrate. The proposal is that when a molecule binds to a receptor, electrons in the receptor might tunnel through the molecule, and the likelihood of tunneling depends on the molecule's vibrational frequency. If true, it would mean that part of your sense of smell involves quantum tunneling, the same trick that lets particles pass through barriers in nuclear fusion. Your nose might be sniffing in stereo, both structurally and vibrationally, using quantum mechanics to help decode the invisible world of molecules. Again, the idea is controversial, but experiments have shown that people, and even fruit flies, can sometimes distinguish between molecules that differ only in vibrational frequency. It's not conclusive, but it's enough to keep scientists intrigued. Quantum biology is still in its infancy. Most of the field is built on bold ideas, tentative experiments, and more questions than answers. But what makes it exciting isn't just the novelty. It's the reminder that the strange rules of quantum physics don't stop at the lab bench. They reach into the feathers of birds, the leaves of trees, and the breath you draw through your nose. It's a humbling thought. The same mathematics that describes the behavior of electrons in a vacuum also underpins the chirping of a robin and the shimmer of sunlight on a leaf. Nature doesn't separate its domains. Quantum effects aren't locked away in some microscopic vault. They're everywhere, woven into life itself. And perhaps, as we learn to understand these quantum tricks, we'll gain not only new technologies, but a deeper appreciation for the ingenuity of evolution. Life, it seems, has always been playing with the strangest tools in the universe. It just never bothered to tell us. At the quantum level, particles do strange things. They blur into superpositions, interfere with themselves, and occupy multiple possibilities all at once. It's the playground of probability, not certainty. And yet, when you look around, you don't see a world made of shimmering maybes. You see a coffee mug, a desk, a cat, hopefully alive or dead, but not both. You interact with a world that feels solid, consistent, and wonderfully predictable. Why is that? Why don't you see tables that are both here and over there? Why don't entire sandwiches exist in a probability wave, only collapsing when you open the fridge? The answer lies in a quiet but powerful process called decoherence, the mechanism that explains how the quantum world gradually loses its quantumness and becomes the classical world we know. Let's start with a quick mental stretch. Imagine a single electron in a superposition. It's not in one place, it's in a spread of possibilities. You can't say exactly where it is until you measure it, and even then, you're only nudging it to choose a location. Now imagine that electron is left alone in the vacuum of space, completely isolated. It stays in that beautiful, delicate superposition. But back on Earth, things aren't so quiet. There's air, heat, photons from the sun, molecules bouncing around, vibrations, fields, and background radiation. The moment your quantum object interacts with any of this, it begins to lose its quantum coherence. The neat mathematical interference patterns start to blur. This is decoherence. It's not that the superposition disappears, it's still there, in a sense. But the quantum system becomes entangled with the environment. That is, all those particles it touches become part of its quantum description. And when that happens, the system stops behaving like an isolated wave of probabilities and starts behaving like something ordinary, predictable, measurable. You can think of it like this. Quantum systems want to be private, but the moment the environment peeks in, they lose their privacy. Not because someone measured them with fancy equipment, but because nature itself is always watching. Air molecules, photons, vibrations, all these things act like tiny, constant observers. They don't collapse the wave function, but they smear out its coherence, making interference impossible. Decoherence is a gentle erosion, not a violent snap. It doesn't require a conscious observer or a big dramatic measurement. It just needs time and contact with the outside world, and it happens incredibly fast. For microscopic objects like electrons or atoms, you can isolate them well enough that quantum behavior sticks around. But for macroscopic objects, things you can touch, see, or eat, decoherence happens almost instantly. The more massive and complex the system, the faster its quantum weirdness dissolves into classical certainty. In fact, decoherence timescales for large objects can be trillionths of a second or less. That's why you don't walk into a room and find your shoes in a quantum blur. Their interaction with the world has already pinned them down to a definite state. In this way, decoherence doesn't destroy quantum superpositions, it hides them. The superpositions still exist in principle, but they're now entangled with so many environmental degrees of freedom that you can't access or reverse them. They become effectively classical, even though deep down everything remains quantum. This also helps explain one of the long-standing mysteries in quantum mechanics. How do we get from probabilities to outcomes? Decoherence doesn't solve this puzzle completely. It doesn't pick which outcome occurs, but it helps explain why we don't see quantum interference in large systems. Why Schrödinger's cat, if left unobserved, doesn't actually shimmer between life and death on your kitchen counter. Decoherence creates the illusion of collapse by bleeding quantum information into the environment. The result is a kind of statistical consensus. The wave function is still there, but it no longer behaves in a coherent, observable way. And this gives us a bridge between the quantum and classical worlds. Classical physics is still a useful tool. It's how we build bridges, launch rockets, and bake soufflés. But beneath it all, the universe hums with quantum rhythms. What decoherence does is gently veil that underlying weirdness, creating the sturdy world we experience. One helpful way to picture it is like walking on a frozen lake. Beneath the surface is water, shifting, fluid, quantum. But the ice is solid and reliable. Decoherence is what freezes the surface. It doesn't eliminate the water underneath. It just keeps it out of reach. And the more connected an object is to its surroundings, the thicker that ice becomes. This also has practical consequences for technology. Quantum computers, for instance, have to fight decoherence constantly. Their qubits are delicate, and even a stray vibration or thermal fluctuation can collapse their quantum behavior. That's why they're kept in ultra-cold, isolated environments to extend their coherence as long as possible. Without that, the quantum advantage vanishes. Decoherence also plays a role in interpretation. Some theories suggest that there's no need for a separate collapse of the wave function. Instead, decoherence explains why certain outcomes appear definite. It's not that the universe chooses an outcome, it's that the alternatives become unobservable due to entanglement with the environment. The tree still falls in the forest, but its echo is drowned out in noise. It's worth emphasizing, decoherence doesn't solve every mystery of quantum mechanics. It doesn't answer why a particular measurement yields a particular result. It doesn't tell us whether the wave function is real or just a mathematical tool. But it does explain why quantum weirdness fades into classical certainty in daily life. It shows us that the world we see is not separate from the quantum realm. It's shaped by it, filtered through a continuous interaction with everything around us. So the next time you pick up a mug or open a door, you can thank decoherence for the fact that it behaves the way you expect, for taking a universe of maybes and presenting it as a firm handshake. It's a quiet phenomenon. No sparks, no flashes, just the slow, graceful loss of possibility, leaving behind the stable patterns we call reality. Imagine setting up an experiment so strange, so delicate, that the very act of deciding when to observe seems to reach back in time and affect what happened earlier. It sounds like science fiction, or perhaps science confusion, but this is precisely what happens in a series of experiments that toy with the very foundation of cause and effect. They go by names like the delayed choice experiment and the quantum eraser, And if you're hoping quantum physics would finally start making sense, well, this is the point where even time itself starts to shrug. Let's begin with a familiar setup, the double-slit experiment. Fire a beam of photons, or electrons, or even molecules, at a wall with two slits. Behind the wall is a screen to catch what comes through. If you don't observe which slit the particles go through, they create an interference pattern, a series of light and dark bands, as if each particle went through both slits and interfered with itself. But if you place a detector to find out which slit each particle goes through, the interference disappears. The particles act like little bullets instead of waves. Simply knowing the path kills the wave behavior. So far, so weird. Now let's get mischievous. In the delayed choice experiment, originally proposed by physicist John Archibald Wheeler, you set up your experiment without measuring the particle's path, but you reserve the right to decide whether you'll measure after the particle has already passed through the slits. In other words, you delay your decision. Will you act like a nosy detective and observe the path, or will you let the particle remain mysterious and wave-like? Here's where it gets surreal. The pattern on the screen will match whatever choice you make, even if that choice comes after the particle has supposedly decided how to behave. It's as though the particle somehow knows what your future choice will be and adjusts its past behavior accordingly. Either it produces an interference pattern, wave behavior, or it doesn't, particle behavior, depending on an event that hasn't even happened yet. It's enough to make a clock melt. The delayed choice experiment suggests that the quantum world doesn't commit to a specific reality until it's forced to. Not just in space, but in time. The act of observation doesn't just determine the outcome, it might determine the history. And then, quantum physicists said, let's make this even weirder. Enter the quantum eraser. In this twist on the double-slit setup, you mark the particles so you could know which path they took, but then you use a clever trick to erase that information after they've been detected. And when you do that, when you erase the which path info after the fact, the interference pattern comes back. The particles behave like waves again, retroactively, as though they never gave up the ghost of uncertainty. This raises a deeply unsettling idea. Reality might not be finalized until all possible information is settled, not just the moment of detection, but also the moment we decide what to do with the information about that detection. It's like a cosmic version of Schrödinger's cat, but stretched across time. Not only is the cat both alive and dead, but whether it was alive or dead depends on a decision made after you opened the box. So, what's going on here? One tempting interpretation is that information, not physical matter, is the true currency of the universe. In the quantum world, outcomes aren't locked in until you ask questions that have answers. Until then, all possibilities remain entangled in a hazy soup of maybes. That doesn't mean time travel is real, or that we can change the past. Rather, it suggests that our usual picture of time as a one-way street might not apply at the quantum level. Events in the quantum realm aren't chained together by tidy links of cause and effect. They're part of a strange, holistic web where outcomes emerge only when the entire system is considered. Still, there are limits. While these experiments are astonishing, they don't allow for communication with the past. You can't send messages backward through time or change what already happened. The results always play by the rules of causality at the large-scale level, but they hint that under the surface those rules are a bit more flexible. Some physicists describe it in terms of entanglement and correlation, not causation. The particle doesn't know what you'll do in the future, it's just that all the pieces of the experiment are connected in such a way that your final setup defines what patterns are visible. Others lean into a block universe interpretation, where all moments in time exist simultaneously, like frames in a film reel. In this view, your choice isn't something that travels backward. It was always part of the grand timeless quantum story. And still others shrug and say, shut up and calculate. The important thing is this: the universe is under no obligation to conform to our common sense ideas of time, cause, or measurement. Our classical intuitions are built for macroscopic objects, rocks and coffee mugs and cats. But down in the quantum mist, the rules are subtler, less linear, less local, and much, much stranger. The delayed choice and quantum eraser experiments don't break physics. They reveal the richness beneath it. They show that the quantum world is not just a smaller version of our everyday world. It's something fundamentally different, playing by a logic all its own. So if time ever feels like it's playing tricks on you, just remember, on the quantum level it probably is. If you were to zoom far enough into the heart of the universe, past the galaxies, past the molecules, past the atoms themselves, you'd eventually arrive at a world where certainty slips quietly through your fingers. A world where outcomes are not determined, but described in terms of probabilities, where particles don't have positions until you look, and even then, they're merely the result of a cosmic dice roll. Welcome to the quantum universe, a place that's not just small, it's uncertain. At its core, quantum physics suggests that randomness may not just exist, but may actually rule. This idea doesn't sit comfortably with everyone. In fact, it made Albert Einstein famously uneasy. He once declared, "God does not play dice with the universe," a line that's been quoted for nearly a century in every philosophical cafe conversation involving physics and fate. But let's unpack what this randomness actually means and what it doesn't. In classical physics, everything behaves like a well-oiled machine. If you know the position and velocity of every particle in a system, you can predict the future with absolute precision. It's a neat, deterministic framework. Like lining up dominoes and knowing exactly how they'll fall, quantum mechanics breaks that chain. It replaces precise predictions with wave functions, mathematical objects that describe all the possible outcomes of a particle's behavior. And when you make a measurement, the wave function collapses into one of those possible outcomes. But which one you get isn't determined ahead of time. It's genuinely random. That's not a code word for "we just don't know yet." It's not the result of human error or missing information. It's baked into the structure of reality itself. The best you can do is calculate the probability of each result and accept what shows up. Now, some interpretations of quantum mechanics, like the many worlds view, dodge this randomness by suggesting that every possible outcome does happen, just in a separate branching universe. So when you measure a particle and it spins up, there's another version of you in another universe where it spins down. No randomness, just infinite outcomes. But even if that's true, you still can't predict which version you'll find yourself in. From your point of view, the experience is just as unpredictable. This raises some deeply philosophical questions. If randomness exists at the foundation of reality, what does that mean for cause and effect? For free will? For the laws of nature themselves? It might feel unsettling at first. The idea that the universe isn't operating on some grand script, but improvising along the way. That there's a fundamental looseness in the weave of reality. And yet randomness isn't the same as chaos. In fact, quantum mechanics is astonishingly precise in its predictions. It doesn't say anything could happen. It says, here's a list of what can happen and the odds of each. When physicists tested quantum predictions like those from quantum electrodynamics, they found agreement with experiments to 12 decimal places. That's like predicting the height of Mount Everest to within the width of a human hair. So even if quantum outcomes are random, the structure of that randomness is deeply orderly. It's a bit like rolling 100 dice and finding that they always sum to a predictable average, even though each die falls randomly. The outcomes are probabilistic, but the behavior of large numbers of particles becomes so reliable that it gives rise to the laws of classical physics. This is why your coffee mug doesn't suddenly tunnel through the table, even though individual particles can. In this sense, randomness is not a bug, it's a feature. It adds flexibility to the universe. It allows for novelty. It might even be essential for life, creativity, and consciousness. Think about mutation in evolution. If every biological event were strictly determined, there would be no variation, no branching paths. But throw in a little randomness, a change in a gene here, a chance mutation there, and suddenly the universe has options. Some of those options lead to leaves, some lead to leopards, some lead to philosophers. In the quantum realm, randomness is the engine of variety. It gives rise to complexity from simplicity, and it does so without breaking the rules, because the rules of quantum mechanics are statistical, not prescriptive. Some scientists and philosophers take comfort in this unpredictability. After all, a deterministic universe can feel like a clockwork prison where every thought, action, and feeling is just the echo of particles obeying rigid laws. But a probabilistic universe? That's one where the unexpected can happen, where outcomes aren't written in stone, but drawn from a deck. Of course, randomness also comes with mystery. When we observe a particle in one state rather than another, why that one? Quantum mechanics doesn't offer a reason. It just gives you the odds. It's like flipping a coin and getting heads. There's no deeper explanation for that outcome, just that it had a 50% chance. And this has philosophical weight. It suggests that the universe is not fully knowable in the classical sense. There's a ceiling to certainty, a boundary beyond which questions don't have definite answers, only ranges of possibility. And yet, we can still thrive in that uncertainty, build technologies from it, discover meaning in it. Quantum randomness also ensures that no two things are truly identical. Even particles prepared in the exact same way will sometimes yield different outcomes. This tiny irregularity, this whisper of unpredictability, is what keeps the universe alive and interesting. So perhaps the universe does play dice, not recklessly, but with an elegance so refined that it creates galaxies, atoms, thoughts, and time itself. And while we may never fully tame that randomness, we can come to appreciate it, not as a flaw in the cosmic machinery, but as the soft hum of possibility woven into the fabric of everything. If quantum physics were merely a set of equations, however strange, however elegant, it might still be considered one of humanity's greatest intellectual achievements. But what makes it truly special is that it doesn't just describe particles and probabilities. It invites us to reflect on something deeper, what it means to know and what it means to be. Because in peeling back the layers of the universe, quantum physics doesn't simply reveal new answers, it reshapes the questions themselves. We tend to think of reality as something solid, fixed, out there, something that exists whether we're here to look at it or not. But the quantum world disagrees, gently yet persistently. It suggests that, at the smallest scales, reality isn't fixed at all. It's a set of possibilities, like dreams waiting for an observer to nudge them into form. When a particle exists in a superposition, it's not just undecided, it's all its possible states at once, a smudge of probability, not a single dot. And when we measure it, it settles on one outcome, as though the universe softly exhaled and chose a story. This raises a quiet, unsettling thought. If observation plays such a crucial role in shaping outcomes, are we as separate from the universe as we once believed? Or are we, observers and all, a part of the grand entangled dance? For physicists, these are technical questions. For the rest of us, they feel almost spiritual. But quantum physics isn't here to offer easy answers. It's not a shortcut to enlightenment or a metaphor factory for self-help books. And yet, it does leave us with something precious: humility. It reminds us that our everyday intuitions about space, time, matter, and cause are not the final word on how things work. That the familiar world we navigate each day is just one version of reality, filtered through evolution, shaped by our senses and stitched together by habit. In this way, quantum mechanics becomes more than physics. It becomes a mirror, showing us the edges of our knowledge, the limits of our understanding, and the breathtaking strangeness of the universe we call home. Think of Schrödinger's cat, not as a literal feline trapped in a paradox, but as a metaphor for the way we live in uncertainty, for how we constantly juggle conflicting possibilities, half-knowns and almost certainties. Whether it's waiting for a medical test result, applying for a job, or simply wondering if it will rain tomorrow, We exist quite often in a quantum state of our own. Hope and fear, expectation and doubt. Possibilities layered gently over each other until time or choice collapses the wave. And maybe that's the secret beauty of quantum mechanics. It's not telling us that the world is unknowable or meaningless. It's just telling us that it's not obligated to be obvious. There's a softness to that realization, a quiet freedom. If certainty isn't guaranteed, then neither is limitation. If the world isn't pinned down until it's observed, then possibility is always alive, flickering just out of view. Even the word quantum has a kind of poetry to it. It comes from the Latin quantus. How much? How much light? How much energy? How much is this or that particle allowed to be or do? But more than that, it's a word that points toward boundaries, discrete indivisible packets, the smallest allowed unit of change. And maybe there's something meaningful in that too. That even in the vast and swirling confusion of the cosmos, there are limits, minimum steps, quiet thresholds that must be crossed. Not everything is continuous. Some things change in leaps. When you dream, you don't do it one atom at a time. You leap into worlds that don't exist until they do. You witness impossible things until they feel natural. And when you wake, you may not remember all the rules, but you carry back the feeling of possibility. Quantum physics feels like that, like waking from a dream and realizing that the world is weirder, wilder, and more wonderful than you'd ever guessed. Of course, this can be a little unsettling. We like cause and effect. We like knowing. Certainty has its comforts. But maybe it's also a little overrated. Maybe it's okay to live with questions that don't yet have answers. To wander in a forest of probabilities without demanding to know which tree is real. Maybe that's where wonder lives, in the spaces between what we can grasp and what we can only glimpse. Physicist Richard Feynman once said, "I think I can safely say that nobody understands quantum mechanics." He meant it as both a joke and a truth. Even those who work with the math every day, who build machines and models from its predictions, will admit that quantum physics is not something you get in the usual way. It's something you accept, like a poem or a dream. It works, it's precise, it's testable, and yet it refuses to be pinned down by ordinary logic. And maybe, just maybe, that makes it more honest. Because the universe was never obliged to be simple, it just had to be. So as we drift now through the quiet ripples of quantum thought, maybe the most important lesson isn't about particles or probabilities, but about perspective. To see uncertainty not as a flaw, but as a feature. To let go gently of the need to know everything, and to rest in the strange, beautiful truth that we are part of a cosmos that is still unfolding, still choosing, still shimmering with possibility. A place where even the emptiest vacuum isn't truly empty. Where time can flex, where light forgets how to behave, and where, in the end, reality dreams too. Thank you for listening, whether you're still wide awake, drifting gently, or already halfway through a dream. We've wandered a long way tonight, through slits in cardboard, thought experiments with cats, rippling fields and mysterious erasers of time. We've met particles that behave like waves, waves that act like particles, and forces that play by rules written in a language we're only just learning to translate. And somewhere along that journey, we began to see not just the oddness of the quantum world, but its quiet beauty. At first glance, it might all seem too strange to be real. A universe where something isn't truly anything until it's observed. Where cause and effect get blurry around the edges. Where a particle can be here, and also somewhere else. But what quantum physics gently reminds us, over and over again, is that the world we know, the one we can touch and taste and measure, is only the surface. Beneath it lies a softer world. Stranger, yes, but also more flexible, more open to surprise. A world built not on certainty, but on shimmering possibility. And we are part of that world, not separate from it. Not merely observers, peeking in from the outside. We are made from these same quantum fields, the atoms in your fingertips, the light that reflects from your eyes, the oxygen in your lungs. All of it obeys the same uncertain laws. You are not just in the universe, you are of it. And doesn't that feel just a little bit poetic? Back at the start, I asked where in the world you're listening from. Maybe you're curled up in bed, listening under a heavy blanket. Maybe you're gazing at the ceiling, thoughts flickering like stars. Maybe you're far from home, or just far from sleep. Wherever you are, I hope you found something in this journey, something soft or strange or simply still. And remember that when we stare into the heart of matter and ask, what is real? Quantum physics doesn't offer us a final answer. It offers us a mirror, a shifting one, a reminder that knowing something deeply doesn't always mean understanding it completely, that questions can be as beautiful as answers, that mystery is not a failure, but a feature. It can be tempting to wish for more clarity, to want the universe to lay out its rules plainly and play fair. But maybe, in this tangled uncertainty, there's a different kind of comfort, a gentle truth that says, you don't need all the answers to feel at home here, because even if the particles are uncertain, the moment you're in is real. The breath you just took, the thought that just drifted by, the weight of your body gently sinking into stillness, that's quantum too, and it's enough. So thank you for giving your time, your ears, and your quiet